I was muted. You didn't get to hear all the clever things I was saying. I felt so clever. I included a mute button in my setup this week, so you don't have to hear me slurping on my beer. And then I forgot to unmute myself, so that's not ideal. But hello. Now I hope you can hear me. Welcome back to another Sunday night Fundamentals of Arduino stream. Here on a Sunday night. I know it's good to be back on a Sunday night. I know there were there's a little bit of confusion with it switching to Monday last week, so thank you again for your patience and understanding. We're back. It's good to be here again. As usual, we'll give people just a few stragglers before they jump in and join us. Give people a few stragglers. I'll just take a breath and slow down. I'll give the stragglers a few minutes to join us before we dive right in. In the meantime, happy to share that this week I am drinking actually a beer with a really cool story behind it. I'm drinking a Turnstile Hopper Juicy India Pale Ale, which was a gift from Lee and Travis, who have been joining us for a bunch of these evenings. They stopped by and dropped off a little beer earlier, so it feels only appropriate that I be drinking their tasty juicy IPA this week. As we talk about, control registers and other related topics, and how we can use them to get a little bit finer control of our Arduinos this week. Hi, Nate, watching on the big screen with the family. Ooh, that's cool. I hope I look at in my setup here. I know you can't see what's going on in all the world. My view of myself is about that big, so I hope I look really good on that view. I hope I look just as good on a big screen TV. But if I don't, I guess we'll spend a fair amount of time looking at the computer screen. So if I'm too big now, I'll be down in the corner in just a little bit. What's the preamble that I always forget? All of the slides that we'll be looking at tonight are linked. You can go to jeff.glass/electronicsbash. All the slides are linked there, as well as all the code that we'll be looking at tonight. Tonight's gonna be one of those nights where we're kind of improving and wrapping our code as we go. So the code that's there is both where we're gonna start, and there's some sort of snapshots of where we're going to get to later in the night. Because I know that copying from somebody's code on a video is not always useful, so whether you're watching this live or in the future, since this is all recorded, if you go to jeff.glass/electronicsbash, all the slides and the code and the links are there, because that might be easier for you to follow along with. It's going to be a fun night. I'm stoked about it, and I'm stoked where I mentioned last week when we talked about hardware interrupts, using little bits of hardware built into the Arduino to suddenly jump to one place or another in our code. This week we're going to be looking at some of the actual control registers, more bits of hardware, more bits of memory that allow us to do that. And next week, we're going to talk about timer interrupts, which are similar in that they allow us to jump spontaneously to a specific place in our code, but they're based on some built-in timers and counters, and they provide a lot of really powerful functionality. So we're going to continue laying some groundwork again, and then we're going to bring it all together next week. Hi, P.S. Janky. Hi, Palmer. A little clippy again. Yeah, it's interesting. I don't know why that is, but here I'm going to turn my gain down by another 6 dB and see if that helps at all. So those of you who are listening, it may have gotten a little quieter, but I'm no longer peaking the meter, so hopefully that helps out. Palmer, not everyone knows each other, of course, in the chat. Palmer is a professional sound human. Palmer, I should just hire you one of these days to do an hour-long EQ and audio gain spectrum, I don't know, gain chain, what's the word I'm looking for? Gain structure, an audio gain structure lesson to make sure I actually get these things a little bit right. Well, do let me know if it sounds better or if it's gotten worse, or if it's bad. I was saying just so I do have a mute button now, so that when I'm sipping my tasty Turnstile Hopper, you don't have to listen to it. But at some point, that does mean I'm going to forget to unmute myself. So just yell at me. It's going to be great. But you didn't have to listen to gulps just there, so I feel like that's good progress. I see our timer has expired. Should we just jump in? Let's just do it. Come over to ye olde slides. So we're talking about control registers tonight and a few other sort of related topics. We're going to talk about the 3 different types of memory that are inside the Arduino, those being flash memory, EEPROM, and SRAM, and what each of those things mean, because they're all relevant to our discussion tonight. We're going to talk about Arduino registers, right? That's the headline of tonight. What is a register? How do we use it? How do we access it? How do we change it? We're going to talk about bitwise mathematics, right? We're going to talk a little bit about how you do math on the specific ones and zeros, the bits of a number. And then we're going to close out tonight by circling back to something that I introduced last week, which is pin change interrupts, which is a method by which we can tell our Arduino to jump to a specific bit of code that we want to run whenever a pin changes from low to high or high to low or vice versa. Last week we looked at what the datasheet calls external interrupts, what I would call hardware interrupts. Which had a lot of like flexibility and sensitivity. You could have them triggered just on a rising edge or just on a falling edge or on any change or so on. And I said last week that like pin change interrupts are a little bit less controllable, and they're a little bit finickier, and they require you to directly access these control registers to set up their parameters. And so we're going to use that as kind of the closing example of our night. Once we know first what a register is and how do we control it, we'll sort of go back to that example and set up some pin change interrupt examples. Cool? So here's where I want to start tonight. So this is a slide that I just yanked from like 3 weeks ago when we were doing our wireless signals talk. And I sort of casually introduced this model of variables having a place in memory. So this slide should look pretty familiar if you were with us a few weeks ago. The idea that when you define something like a byte or an int or a long, the compiler, which we met last week, picks an address in memory, picks a byte or 2 or 4 or more, and says these are going to be the places that hold the data associated to this name, my byte, my int, my long, that the programmer has given us. And those are going to exist at what we would call a specific address. The locations in memory are essentially numbered sequentially from 0 to however many there are. So we might say that my byte in this case exists at address 185. My int exists starts at address 186 and also exists in 187 because, as we know, an integer in our case is 2 bytes long. A long starts at 188 and so on. This model hopefully feels a little bit familiar. What I want to do though is sort of clarify a little bit. This model was good enough for our purposes 3 weeks ago, but I want to clarify a little bit like what this actually represents in a more physical sense inside the Arduino. I sort of hinted earlier that there are 3 types of memory, and they all behave a little bit differently, and this is only one. So I want to show you where this fits into the bigger picture. So the 3 types of memory, let's start with flash memory. Flash memory, of which you get 32 kilobits of code on, this is all, I should say, for a lot of this evening is going to be based around the Arduino Uno, the ATmega 328P. It will also be true of an Arduino, like a Pro Mini. I was looking around to see if I had one of, right, oh, I do, here we go. It's one, there's a gutted moving light here. Arduino Pro Mini, anything with a 32.8 on it is going to have all these stats. Of course, if you have a different species of Arduino, like a Mega or a Due or something like that, the exact numbers will vary, but all of these concepts translate directly. So if I was saying, like, this is how much space you get, just know I'm assuming Arduino Uno. Your experience may vary depending if you have a slightly different type. But in general, this will be true. We have 32 kilobytes of flash memory on an Arduino Uno, which is where the code is stored. When you upload code to an Arduino, when you're in the IDE and you hit that upload button, this is where ultimately the ones and zeros that your code becomes are stored in the flash memory. Flash memory you can think of essentially like a flash drive. It's the same, they come from the same thing, they're both the same type of memory. And much like a flash drive, you don't need to have power supplied to it in order for that memory to preserve your data. In this case, to preserve your code. So even when we unplug our Arduino from our USB port or our battery or whatever, that code is not going to go away. I think this slide basically says all these things I'm saying in words. It's where your code lives. So there's 32 kilobytes of flash memory in your Arduino for your code, but we don't quite get to use every single little bit of it. Right at the end, there's a little section, and most of the time for our purposes, it's 256 bytes that are taken up by the bootloader. That's just a little extra program that is essentially preloaded onto the Arduino that allows us to use a USB cable or a serial port to upload code onto the Arduino. It's not something that the 32.8 sort of natively can do, so we permanently load a little program just into the end of our code section that says, hey, if you get this kind of signal over the serial port, that's program information. I'm going to want you to write some bytes to the rest of the flash memory as they come down the pipe. And this little program sort of helps us do that. So, what else? Oh, it's sort of academic. The memory model we were looking at the other day, all of the locations had values in bytes, sort of at 8 bits of information at each location. In Flash, they're 16 bits at each location in memory. You don't actually need to know that. I just think it's kind of interesting. Oh, the data sheet says you get at least 10,000 write/erase cycles per location in Flash, which sounds like a lot, but if you think about a debugging process where maybe you're uploading code 100 times a day, you only have 100 days of that before your Flash starts to not really be writable in a reliable way at those particular locations anymore. I wouldn't let this slow you down from uploading code as frequently or as often as you want to a specific Arduino Uno, but let's say, if you have sort of one that sits on your workbench and you use it for everything multiple times a day, after a couple years, if it seems like the uploads are being a little sketchy and not successful, it could be that you've worn out your Flash, and that's just part of the cost of doing business. Again, don't let that slow you down, but it can happen. So that's the first of our kinds of memory, is the flash memory. The second type I want to talk about is the EEPROM, which stands for Electronically Erasable Programmable Read-Only Memory, or EEPROM, as we'll call it. You get 1 kilobyte of this on an Arduino Uno, on a 328. And again, like Flash, it's data that is not erased when you remove power from it. It's also data that is not erased when you upload a new program. It lives in a sort of a different place in the chip, and when you upload new code, the EEPROM is preserved. So this is a great place to hold a couple different kind of things. You could hold data that you've collected in the field, right? If your Arduino has a sensor on it and is taking say a temperature reading every 5 minutes, you could save those readings to the EEPROM, and later you could upload a new bit of code that specifically said, okay, take bytes out of the EEPROM and say spit them out over the serial port to my computer, and I can do something with them there. It's data that exists persistently outside of the flash memory. It can also be really useful for things like configuration data. For parameters that you're not positive about when you're writing your code and you want your user to be set in the field. So let me show you a little example here. What's going to be best way to show you this? I think this view still works, although it's a little silly. So you might remember this signal generator that I've showed off before. A little hard to see there, but it's based on an Arduino Nano, I think, inside of there. A little hard to see. Let's zoom in a little bit. You can see it's set to 1.8 megahertz there. There's nothing really to see there. I'll take this view away and I'll just talk at you. The gist of the example is it's a signal generator. It puts out an adjustable frequency that the user determined, and it has basically a module in it that you talk to over a serial port from your Arduino and say, hey, module, please be at 1.8 megahertz now. Please be at 10 megahertz now. Please be at 50 megahertz now. And the module just goes, okay, and on one of its little pins, it puts out that frequency. From the factory, it was running about 0.5% low, about 0.5% slow. So I'd say, hey, please be at 1 megahertz, and it would say, okay, I'm at 1 megahertz, but it would actually be putting out 990 and something kilohertz, right? A little bit low. So what I did is I wrote a little routine that said, okay, the user can press this series of buttons to get into this mode where they can adjust how off this module is. I said, okay, dial it up by 0.5% until I could see on my frequency monitor that I had sitting next to it that my, 1 megahertz was 1 megahertz. And then I had that routine save that offset, save that calibration data to a place in the EEPROM, which means that not only is that information preserved when I turn the power off, I have it when I turn the power back on and it boots up, it looks at that place in EEPROM, and if there's data there, it says, oh, okay, well, we must have done some calibration before. I'll load that offset back in so I stay accurate. It also means that as I continue to refine the code for it, add new modes, add new offsets, incorporate nerdy ham radio functions into it, as long as I wasn't, as long as I was using that same place in EEPROM, I could, that data is stored in the physical device itself. I didn't have to worry about sort of readjusting that data every time I uploaded that code. It's more or less permanently inside of our microprocessor until we change it. So EEPROM, good for persistent data collection and configuration data. If you're curious, I don't want to get too down into this demo. Oh, hello. Camera got a little wacky from showing you the signal generator. But just to call it out, reading and writing information to the EEPROM is super simple. There's examples in the Arduino IDE examples folder if you want to play around with them that are pretty good. The gist of it is you sort of have two different species of read and write commands. You can do this EEPROM.read or .write, which writes a single byte to a place in memory. If you use the put and get commands, it'll work on a multi-byte variable. So say you wanted to write a long integer. Let's say you were wanted to record the time from millis until something happened to a place in EEPROM. You would want to use EEPROM.put, and that would store all 4 bytes of that long into a contiguous place. And if you were to get that later, it would suck those 4 bytes back out and turn them back into a long for you. So just to show you a real quick example. This, I should say, so all the code is on the website except for these couple of examples because they're so brief, and they're actually, the ones that are in the Arduino IDE are better. But just to give you a real quick sense of how the EEPROM module works, you use this EEPROM.write function with an address in EEPROM, so in our case, a value from 0 to 1023, which is 2 to the 10th, and a value to put there. Actually, this should be a put. So it'll put an integer there, right? And that will store that value in EEPROM, and the corresponding function is EEPROM.read. So we give it an address to look for in that same range. We read it out, and we can do something with it. It could be calibration data. It could be user data. It could be, has this code been run before? It could be a version number. There's lots of things you could do with it. Anyway, like I said, that's not the main thrust of tonight, but I did want to point that out because it's kind of cool functionality, and you might want to go and play around with it. So the third type of memory, and the one we're going to be living in the most tonight, is SRAM, Static Random Access Memory. Static in this case just means that it doesn't need to be constantly refreshed. This separates it from what's called DRAM, or Dynamic Random Access Memory, which your processor essentially has to, the values that are stored in it are constantly deteriorating. And so with some frequency, your processor is meant to, for every address in that RAM, read the information out and write it back in afresh so that information doesn't sort of degrade and fade away. SRAM, static RAM, doesn't have that problem. We can sort of write to it and know as long as we have power, that information is there. When we unplug the Arduino, when it loses power, all of that data goes away and it defaults to 0. We don't maintain that data in between individual runs and sessions. This is where this is the equivalent of this memory model that we were looking at last time that holds our variables, our integers, our various other things all live inside of SRAM. Any temporary value, any variable is going to live in this SRAM part of memory. A few other things in addition to variables live there. You use a little bit of SRAM to keep track of things like when you jump from your loop into a function, the Arduino needs to have a way to remember, say, where in your loop you came from, so that when the function is done, it can go back to that place in the loop. That little chunk of information has a home, essentially a variable that you don't need to worry about inside of SRAM. You might also have global and static variables, so variables that you define at the start of your program, as opposed to inside of a function, live in SRAM. Local variables that you define once inside of a function, live in SRAM, and so on. And like I say, so it's when you lose power, all of your SRAM data, all your variables go away. And this is something we're pretty much used to, right? When we are setting up our code, we're assuming that we have to set the values of all of our various variables every time the code runs. How many button presses is this going to take? How long are we going to delay in this function? All these various parameters, nothing is preserved in the variables. Every time the code runs, it resets these variables in SRAM. So in addition to these various things, variables, settings, stack pointers that point from where functions came from, and so on, we also have 256 bytes of registers. You see, I made you wait for it, but we're less than 20 minutes in, and we're already getting to the point. We're figuring this out 18 weeks in here. let's see. So you can see in our little slide here, in SRAM, in addition to our variable storage space, our 2 kilobytes of storage space, we have 32 general purpose registers, and then we have 64 plus 160 I/O registers, input-output related registers. The difference between the normal ones and the extended ones is academic, and it takes care of it all behind the scenes for you. But essentially, we have these 256 registers, 256 places to deal with. And like everywhere else in SRAM that we've talked about, each of those registers holds a single byte value. So let's talk a little bit about what those registers are. A brief aside, the ATmega 328 and 328P, as we talked about a few weeks ago when we talked about like moving the Arduino chip from the Arduino to a breadboard or programming externally or using an ATtiny or all those fun things, there are a variety of objects that are a lot like our friend the 32.8, but a little bit smaller. So we have the 16.8, the 88, and the 48, and the only differences between them are how much of each of these types of memory they have. So down at the bottom here is our friend the 32.8P, which has 32 kilobytes of flash, a kilobyte of EEPROM, and 2 kilobytes of RAM. If we go all the way to the other end of the scale, we have the ATmega 48A, which has 4 kilobytes of flash, 256 bytes of EEPROM, and 512 bytes of RAM. So for a simple program that doesn't take up much program space, doesn't need much EEPROM, and doesn't need much RAM, we can drop in one of these 48A microcontrollers and it will work exactly the same in every respect. It just has a little bit less storage space, which we might not need. This last column over here is, if we want to get technical, the last difference between the two of them. It's essentially this interrupt vector size is when you trigger an interrupt to jump to a specific point in your code, the larger Arduino, the larger ATmega variants allow you to essentially run one bonus instruction before it jumps away to your interrupt. They have a two instruction words per vector, so you get one to do something and one to jump away to your code. The smaller ATmegas only get one. You basically, when you trigger an interrupt, you have to jump to that code right away. This is not a huge issue for most of the things we are doing, but if we're going to be technical, and I assume since you're here with me on Sunday night, you would enjoy being technical, that is the last difference between these various sizes of ATmegas. So let's talk a little about those registers that I mentioned. So we have our 32 general purpose registers. We have our, 224 I/O registers, and then they're followed up by SRAM, our general purpose variable holding RAM. The 32 general purpose registers are sort of not the kind of register we're going to be talking about tonight. These are places in the Arduino's memory that it stores values temporarily to do things with them, to perform math, to add and subtract, to return them from functions, and so on. When we looked at Godbolt at the Compiler Explorer last week or a couple weeks ago, last week it must have been, we saw how under the hood, what the Arduino is running is not so much like code that looks like English, but instructions that look more like this code down at the bottom here. You know, LDS R18 with a variable, LDS R19. This R18, R19 are these general purpose registers, basically places to copy a bit of information into a place, copy some other in, and then I can do very basic operations like adding, subtracting, comparing, and so on. So we generally, at the level of code that we're writing, are not going to touch these general purpose registers. They're hidden from us. They're taken care of under the hood by the compiler and the processor itself. What we're interested in is the I/O registers, and these basically control all of the major parameters, workings, input-output functions of the Arduino itself. So things like whether a pin is an input or an output, whether an output is high or low, or similarly, if you read from a value in a specific register, it will tell you whether a digital input is being held high or low. It will set up these timers that I keep alluding to, and which we'll finally get to next week, how they can be used to count and trigger things, how we set up actual interrupts and their triggers under the hood, peripherals like UART, our serial port, EEPROM access, SPI, I2C, other ways of talking to other chips. There is, if you're interested in poking around, and I encourage you to go look at the datasheet for the ATmega 32.8P, because I just will gladly assume that you are all nerds out there. I think that's a fair assessment. If you come to the end of the datasheet, you get this register summary. Here, let's zoom you in a little bit there, which is a big list of all of the various registers. So this is their locations in memory and their names down the side here. So there's a register called TWAMR, TWBR, OCR2A, and so on. Don't panic. We're going to talk about a lot of these ones and what they specifically mean, but if you wanted to like go and start exploring, this is the map of the whole world of I/O registers inside the Arduino. So what is a register? A register is a place in memory, a place in SRAM, and as we know, places in memory mean a byte with an address, 8 bits of information with an address that we know where it can be found. Each register has a name. Usually it has like a nice English name that we can call it by, and then like a kind of confusing string of letters that means that name. We'll see some examples in just a second here. The register will have an initial value. It's almost always all zeros. When the processor resets, almost all these values will default to 0. The bits themselves will often have names, and we'll see that in a second, and it will always live at a fixed location in the memory of the Arduino. Bits are numbered from 0 to 7, counting from the least significant. Let me just show you an example. So this, let me get rid of that. This is just a little thing that I snipped out of the datasheet. We'll look at this register in more detail. I just wanted to show you how this diagram is working as we see it. So this is just a little thing I snipped out of the datasheet. It says the name of this register is port D, the port D data register. So I know I'm going to call it the port D data register, but for short, and when we write it in code, we'll need to say port D. And the name is also over here. It, like all registers, has 8 bits, 0, 1, 2, 3, 4, 5, 6, 7, and the bits of it are called port D0, port D1, port D2, and so on. So for this port D register, and I know I haven't explained what the heck a port D is, the bits are pretty logically numbered, right? There's 7 related bits doing something in whatever a port is, right? That may not always be the case for every register. Some registers are more like collections of individual bits of information. So for example, like this MCU-CR, which is a control register that sets some various parameters how the Arduino is working, its individual bits are the IVCE, the IVCell, the PUD, the BODSE, and BODS, which control, I think, respectively, some functionality of how interrupts work, some functionality of how the brownout detection system works, which is if the voltage falls too low, some things will stop happening. I don't remember what the PUD bit is, but this is only to say that a register might be a collection of 8 related things, and is in the case of like this particular port D register, or 8 individual things that are sort of loosely grouped together into a single byte in memory. We'll also see not all of the bytes are used in every position. In this MCU-CR register, positions 2, 3, and 7 don't actually mean anything to this particular processor. Maybe there's something that the developers of the microprocessor were saving for a later date, or saving for a larger version of this same processor. That's actually a relatively common theme, is that, you know, a manufacturer will have developed a sort of small version of this processor, and then they'll develop that into a larger, more expanded version, and they want it to be essentially compatible with the smaller version. And so the smaller version, when they develop it, will have a lot more of these register spaces than they need, and just leave them unoccupied. And the larger version of the processor will say, okay, well, all of these registers that were unused in the small one now mean things, because we have 4 serial ports and 6 different ways of talking to other chips, and now we need more ways to sort of set their parameters. Questions so far? I think the next thing we're getting into is diving into just a bit of an example, which I think will be useful, but I just want to make sure we haven't lost anybody so far as we're talking about the different types of memory inside an Arduino, or the rough idea of a register being 8 bits inside of a thing. Yeah, as always, I know there's a little bit of a lag, so you might be already typing the questions. I'm going to pause a sec, take a sip of my turnstile hopper, and then plow ahead. I didn't mention earlier, Lee and Travis, to whom I have to thank for this turnstile hopper this evening, did some research through the past episodes as to what kind of beers I have been drinking each week, and they settled on Juicy IPA as the most thematically appropriate, and they're not wrong. They got it right in one. So thanks, Lee and Travis. I don't think they're with us tonight. I know they're out in the burbs, but I really appreciate it. It was very, very nice. All right. Yeah, they're savvy. They're real. I mean, there are people, right? They're nerds. All right. Let's plow ahead. So let's do. This is going to be our example hardware for this evening. Should look pretty familiar. It's going to be. Oh, excuse me. I guess the mute functionality can be used for when I'm constantly burping up juicy IPA. This is the hardware we're going to use this evening. It's going to be an LED and a resistor connected to digital pin 2, and a switch or a button connected to digital pin 5. Ooh, that's fully populated. Palmer says the whole topic is completely new, so I'm just trying to absorb what this stuff is. Cool. Yeah, this is like, definitely going to be a new dive into topics we haven't seen before. And please do ask questions. This is another week. I mean, I guess I say this every week, but we did it last week where I think we have a considerable amount of time. So I am happy to pause, to detail, or to do examples over again, especially as we start getting into like the code and details portion of this evening. So please do flag it, because I'm happy to try to explain stuff in a different way if it doesn't gel the first time. This circuit, I hope is relatively familiar. Let me show you the code that we are starting with. If you're playing along at home, this will be the LED button example from the website. The code itself is very, very simple. It's just gonna basically, my philosophy of how we learn this stuff is like, if you're learning a new skill, a new technology or something, start by replicating something you can already do with the new technology. The image that comes to mind is always like, when you're learning German, you don't, in 10th grade, let's say, not that I did, but let's say you're learning German in 10th grade, you don't also learn how to write a sonnet at the same time. When you learn German, you first learn to say like, good morning, my name is Jeff, and I go to school in a place, right? You learn things you already know how to do in a new form. And once you've mastered that new form, then you can start expanding your abilities. So we're going to take a very simple bit of code and use our new register knowledge that we're going to learn tonight to do the same thing in a different way. Oh, Nate has a question. If the flash goes bad on Arduino, can you replace the 32.8 to replace it? Yeah, you totally can. Essentially, all of those parts of memory live inside the processor itself, the 32.8. So yeah, you could just replace that chip. You would want to, before or after you do, you would need to burn the bootloader onto it, that little section of code at the end of the flash that helps us upload code onto the Arduino. Nate, I don't remember if you were with us for the minimizing the Arduino week at that point, but the gist of it is, and it's kind of germane to tonight, right, that little extra bit of code that lives at the end of flash, right, that helps us, where were we? That helps us upload our code onto the Arduino. When you buy the chip, that code is not already uploaded typically, although if you go to a vendor like Adafruit, you can buy chips with the bootloader preloaded, which can be kind of convenient. Otherwise, if you sort of buy them raw from the factory or from DigiKey or Mouser or something, you have to go through and basically do a separate process to burn that little bit of code to start with, and then the USB programming that we know and love works, if that makes sense. So let's see. So let's dive in a little bit to, where were we here? Registers. A register is 8 bits, is a byte, has a name, all that stuff. All right, so here's our circuit. Oh, I was going to show you the code. It's really very simple. We're going to define places where our LED and our button are connected in our circuit. In our setup here, we will define the button as an input pull-up and the LED as an output type. And then our loop is going to be really dead simple. Every time we go through the loop, we'll take a reading from that button pin. If the reading is high, so in our case that button is being pulled up so the button is not pressed, turn the LED off. Otherwise, if the button is being pressed, turn the LED on, right? And then we'll just sort of loop through this as fast as we can. So when I upload this, hopefully if everything's gone well and I haven't made a typo in the last few days, then when I take my circuit here with my LED and my button, when the button is held down, the LED turns on, and when it is not held down, the LED turns off. It works. That's pretty great. So hopefully that code is relatively approachable, right? It's a relatively simple function, but this will be a good basis to give us some entry point to working with the registers of the Arduino to essentially do the same thing. And then we're going to build some more knowledge on top of that. Cool? So the first concept I need to introduce to you is a thing called I/O ports. This is one of the functionalities of the ATmega 32.8 that the Arduino environment kind of abstracts away from us. The pins on the Arduino are named and numbered in a somewhat inapproachable way. And so when the manufacturers of the Arduino said, hey, we want to make this as user-friendly as possible, we're just going to call them digital 0 through 13 and analog 0 through 5. But under the hood, they're organized not as 0 through 13 and 0 through 5, but into these 3 different ports. And each port is just a collection of these pins with a name, up to 8 pins in a specific port. They're laid out in a little bit of a confusing way if you're thinking of them as, these digital pins that we know and love. But just to call them out here, and I'll show you this in visual form in a second too. Port B represents digital pins 8 through 13. Port C represents our analog pins, and port D represents digital pins 0 through 7. There's some behind the scenes reasons for why there's not 8 pins in all of these. For example, in port B is digital pins 8 through 13, and also the 2 pins that our crystal oscillator is attached to. So we don't mess with those. But the easiest way to see this is on our Arduino pinouts that we've looked at a few times in the past few weeks, and I've just zoomed into one side of it here so we can see a little better. We can see our digital pin numbers that we know and love, 0, 1, 2, 3, 4, and so on. But in this column here, we can also see them called PD0, PD1, PD2, and so on. We have PB0, PB1, and so on. Those are those internal port names I was talking about. So we can see that digital pins 0 through 7 all belong to this PD group. They're port D pins 0, 1, 2, 3, 4 to 7. Pins 8 through 13 are ports B, 0 through 5. And then we have a couple of analog pins up here, and you can see that those are in ports C, 4, and 5. And if we were to look at the other side of the board, we'd see port C, 0, 1, 2, 3, and so on. So just different names for the same thing. But when we're working with the sort of registers under the hood, the registers don't know anything about what the Arduino environment is calling them. It just knows what its internal names are. So when you hear, I would say you don't have to memorize any of this. Every time I'm like, okay, I've got a button hooked up here. What port, what pin? You just go look at the pin out and say, oh, that's port D pin 6, right? So don't memorize it, just a different name for the same thing. So for our example today, we know we have, and I'm going to always have to double check which one's which. We have an LED attached to pin 2 here, or in other words, pin PD2 or port D pin 2, and a button attached to digital pin 5, which is the same thing as port D pin 5, or PD5 in this case, right? Sort of makes sense. 2 different names for the same thing, how that information is organized under the hood. All right, so this is going to give us the ability to introduce our first register that we care about. And I'm going to introduce this idea, and I'm going to show you in code how we use it. So the data direction register controls, very literally, whether a pin is an input or an output. There is a data direction register for each of those 3 input ports. So there's a data direction register for port B, for port C, and for port D. And if there is a 0 in the corresponding position in the data direction register for that port, that pin is an input. If it's a 1, that pin is an output. Really, when we're doing things like pin mode input and output, what we're actually doing under the hood is changing the values in these registers. It's not that these registers somehow sort of represent that functionality. They are that functionality, if that makes sense. So, and like I say, there's 3 different registers, 3 of these different data direction registers. So this is for example, the one we're looking at here, the port D data direction register, and its short name is the DDR-D, the data direction register for port D. We also have a DDR-B and a DDR-C for the other 2 ports. So as usual, I've put a little Arduino box down here to remind me that this is the point I wanted to jump to the code. So let's jump to the code, and I'll show you how to work with this register a little bit. So, and again, just starting from that same basic code before. So now we're going to use this data direction register to replace a little bit of our code in our setup function here. So rather than do pin mode LED, what I really would like is for the to directly access the values in this register that make the LED an output and the button an input, right? So we know that a particular pin is going to be an input if its value in this register is a 0, and if it's a 1, it's going to be an output. So rather than saying pin LED output, what I really would like is position 2 in this register to be a 1. Does that make sense? So very literally, if position 2 in the data direction register for port D is 1, then pin 2 on port D is an output. Does that track? I know I always am like, doesn't everyone make sense, right? But that's the critical thing, is these bits represent functionality or configuration of the Arduino. So let me say that one more time. If position 2 in the data direction register for port D is a 1, then pin 2 on port D is an output. That's just by definition of what this data direction register is, right? So how do we set that? In our code, instead of saying pin mode LED output, what I can say is port D, and let me zoom in a little bit here because I know it can be a little hard to see. Where's my code there? Port D equals, and I'm going to give it a direct binary number, right? Rather than trying to calculate the base 10 equivalent of some number, what I really know is I want this data direction register to be 000000100. So there's a 1 in this 2 place here. So I can write a capital B, and the program will know I'm writing in binary, and then just say 000000100. Did I get that number of things right? Yes, I think so, right? And that will set port D to this value. So that register will now hold the information that pin 2, where LED is connected, is now an output. So if I upload this code, and I haven't made a typo, hopefully the functionality should be exactly the same. Oh, haha, it's not. I know what's going on. Let's see. I'm gonna come back here, and so I have a functionality for turning things from an input to an output and so on. We haven't gotten to input pull-up yet. So what I'm going to do is just set this input pull-up command come after the port D command, because we'll see how to do pull-ups in a second here, but I haven't shown you yet. So let's upload that code there, and if I haven't made a typo, hopefully things work this time. This is good. I don't want the demos to go too well too early. Let's see. So it stays turning on, although very weakly there. Let's see, did I get... It's certainly possible I've goofed up which connection is where at some point in this evening. Pin 2 is an output. Port D... Oh, I'm sorry. That's the wrong register. We've been talking not about port D, but DDRD. There we go. Let's try that one more time. There we go. There's our pin again. So as usual, the issue was Jeff Glass doesn't know how to type things, which is fine. I'll cop to that. So we've replaced this pin mode LED output statement with DDRD equals this binary value, and this 1 here represents the fact that that LED is going to be an output. Now pin 5 on port D, which is where our button is an input by the fact that this bit right here is a 0, but it's not a pull-up yet. So let me jump ahead to the next one, and we'll show you a couple things combined into one, how you enable pull-ups on pins. We have another register to take care of that. It's amazing. It's the registers night, and we're talking about registers. It works out really well. This is why I was getting a little bit confused. The next register we want to talk about is these port registers. Just like the DDR register, there is a port register for each of our 3 input and output ports. So this one is going to be the port D data register. There's also a port B and a port C data register. And this register actually does double duty. If the pin that it is associated to, and remember, so each of these bits in this port register 0 through 7 is associated with one of our port D pins, which we would know as digital pins 0 through 7, right? Each of the bits in this port, if the pin is an output, setting that bit to 1 is the same as doing basically digital write high on that pin. Sets that pin to 5 volts output, sets it to high. If it's a 0, it sets that output to low, to 0 volts. If the associated pin is an input, instead, this bit means if it's a 1, we enable the pull-up on that pin, or if it's a 0, we disable the pull-up on that pin. So this port, since a pin can only be an input or an output, this port register, this port data register, is kind of serving 2 functions, depending on whether that port is an input or an output. This is why in older versions of Arduino, especially if you're looking at examples online that maybe are from a few years ago, you don't see this input pull-up type of pin mode that we're such a fan of now. What you see instead is something like, I'll just show you the equivalent. What you would see is pin mode, button, input, and then digital write, button, high. Right, which doesn't really scan, right? It's an input and then we're turning it high. This is basically enabling the pull-up on this step. And the reason that that worked was because just like if you had an output, doing this digital write function would literally behind the scenes just go in and set one of these bits from 0 to 1, which if it's an output turns the variable on, right, turns the pin high, but for an input, that same bit enables the pull-up. And then they realized, like, this is kind of a confusing way to write it. We should just, like, make a little shorthand that has this input pull-up functionality that does both of these things. But that's why if you see in all those weird examples, people doing digital write to an input, that's why. So what I would like to do is I'm going to use this port register in a couple of different places. I'm going to first use it to enable the pull-up on my button, and then I'm going to use it to do the output step, do the digital writing to our pins. So here's our pin mode button input pull-up. So let's replace that code as well. I muted myself. Oh no! How long have I been muted? What did I not say? Oh, that's gonna be a real problem. Maybe my mute button is too close to the typing of things. What was the last thing anyone learned? And well, actually, what's the last thing anyone heard? If you told me the last thing anyone learned was like week 1, what is an Arduino? Actually, I guess I wouldn't be that sad. But clearly there are some things to iron out here. Oops. Well, here, I'm going to deliberately mute myself this time and take a little conciliatory beer sip while we figure out where I need to pick back up. Very good. So let's see. So here we were. So we commented out this function here, and we replaced it with this statement: port D equals binary 00100000. And this 1 in position 5, we know there's a 1 in this position 5 of this port here, which means since that pin is already an input, that's going to enable the pull-up on that pin, right? So we upload the code, come back to the table, and hopefully things still work. I'll make sure everything's uploaded, and everything still works. So we can see that pull-up on that pin is still functioning great, right? All right, so let's do the other thing we can now do with our port data register here, which is replace our digital writes with direct connections to that port. So instead of saying digital write LED low, really we know a pin is turned off when the corresponding bit in the port register is a 0. So that's pin 2, so I want a 0 in this place. So instead of doing digital write LED low, I'm going to do port D equals binary 000. So what did it start as? Yeah, so equals 000000076543210. That's often how I figure out what places these things are in, is I just count myself down from 7 to 0 as I type them in. And here, let me put that digital write back in here, and I'll comment it out so we can continue to compare, right? So that command is going to set this bit to 1, which is going to enable our output here. And that should be low. And down here, I will also comment out this digital write, and I will turn on that LED by saying port D equals binary 0000010, yes, and it should be off up here. That should be all zeros. It should be on down here. This should have a 1 in this place, which will turn on this pin, which, because that pin is an output, will set the output to high. Little bit of did a little bit out of order, but hopefully that's all tracking, right? So we're using these commands to just set the value of this thing called port D to this binary value. A little point of order. When we say port D here, we can basically treat it like a variable. It's technically not a variable in that it doesn't live in SRAM, it doesn't live in SRAM where your variables live. It has a permanent home, so it doesn't take up any extra memory to put it there. But we can we can assign to it, we can use it in if statements to query it, we can do all kinds of things. So it behaves essentially like a variable here. And since it always is 8 bits long, it's 1 byte long, writing the value to it in this binary way where we precede it with a B and 8 binary digits is a really easy way to access it. So I think if everything's gone right, I'm going to reset here, right? And now we'll see that actually things are somewhat broken. You'll see, it's interesting, if you see if I reset it, the LED turns on by itself, but not right away. There's a little bit of a lag. And this is because I've made a deliberate goof in the code. So this is a perfectly valid way to set the output state of that LED pin by writing zeros to this port, or writing ones to this port. Totally fine. Except, of course, that port D doesn't just represent our output states. It also is representing whether things have a pull-up on them or not. I have this 1 up here in port D representing the pull-up on our button pin. And by writing this hard value to it, I'm blasting away that pull-up by writing a 0 to that position. So there's a couple different things we could do here. There's an easy way and there's a learning way. And I'm going to do the learning way. So some of you are thinking is like, okay, well, really, that bit should just be a 1 in both of those places in position 5 here to maintain that pull-up on in both of those pins. And that's true. Like, that makes things work. But what I want to show you instead is a different way to think about this problem. When I want to turn that LED on or off, what I really want to do, instead of setting the whole port to something new like I'm doing here, right? I'm taking this whole byte and blasting this whole new byte value into it, and then I'm blasting this whole new 8 bits, whatever was in port D, screw that, it's these 8 bits now. What I'd really like to do is actually just say, hey, I don't really care what else is going on. I just want to make sure this bit in position 2 here is off or on. I want to set it to 0, or I want to set it to 1. And I'd really like to not touch anything else that's going on in here, so that, when I come around later and I add another button and it also has a pull-up, I don't have to come and figure out where I've written to that port and which pins have pull-ups or when. If I'm using a pin for a couple different things, maybe it's an output at one point or it's a button later. It seems like a lot of a mess. Really, what I would like is a way to set or make into a 1 a specific bit in a byte, or a way to clear that bit, which is just another way of saying I want to make it a 0, or maybe I'd like the ability to flip a bit. Say, hey, if it's a 1, make it a 0. If it's a 0, make it a 1, right? That sort of makes sense. That's really what we'd like to be doing here, is instead of overwriting port D with this new value that we've kind of have to track through and make sure is right, what I'd really like to do is say something like, if I were to do it casually, I'd say set bit 2 of this port to 0. Right? And in this case down here, what I really like is to say set bit 2 of this port to 1, right? What is the cleanest and best way to do that? And if some of you guessed that it might be related to Bitwise Math because we previewed it in the topics we were talking about tonight, you guessed it. I need another sip of beer because we're going to dive into some cool stuff here. Is anyone drinking anything fun out there tonight? Again, never any pressure to drink. Water is totally good. Hydration is important. But if you are drinking tasty beers, always curious. Okay, let's dive in. So let's remember, as we go through this, our goal is to be able to make a particular bit in a byte into a 1 or a 0, or maybe we want the option to flip it. And the terms of art there are usually to say we set a bit when we want to make it a 1, we clear a bit when we make it a 0, or we flip a bit when we wanted to say, hey, if it's 0, make it 1, if it's 1, make it 0. You'll see these terms set and clear tossed around a lot. They just mean make it a 1, make it a 0. Ooh, let's see. Ooh, Love of Hops from Two Brothers, Chris. I don't think I know that one. A Mango White Claw. It's the summer of seltzers. We've kind of settled into being a Truly household here, but super refreshing and super fun. Water Nights, also very good. I applaud. Hydration is key. So here's how we're gonna approach toggling, flipping, setting, clearing bits within a port, within a byte. And to do that, I want to take just a little bit of a step back and make a little bit more formal something I've been talking around, honestly, since I think week 2, which is a little bit about just logic, things to do with true and false values in code. And I want to sort of preface it by saying, for today's purposes, true is the same as high is the same as 1, and false is the same as low is the same as 0. And this will all become clear in the examples, but I want to preface it with this because that is true in the Arduino environment, but it's not necessarily true in every environment or in every situation. There are lots of situations where, especially in signaling protocols, where a low level, a 0 volt level, represents a logic 1. Or in something like RS-45 that we talked about a few weeks ago, you have a pair of voltages which are different in a specific way for 1 and different in the reverse way for 0. And so there isn't really a correspondence from high to low to 1 to 0. But for our purposes tonight, talking about logic, true is 1, false is 0, true is high, false is low, and so on. And that's generally true pretty much wherever we are in the Arduino environment. I just thought it'd be worth calling out. And again, this is kind of just making more formal something that we've been tossing around a little bit here, but we're going to actually introduce and make a little more formal some logic operations, right? And you might remember these from like a high school or college math class. The idea that a logical operator takes some inputs and decides based on them whether the output should be true or false. Could be a single input or multiple inputs or so on, but at the end of the day, we're deciding whether the total operation on some inputs causes a value to be spit out as true or false. And we're sort of going to talk about these in sort of like the logical sense and then how they translate into Arduino functionality. And we've seen a fair number of these already. Things like the idea of a logical AND, right? Which takes a couple of inputs and the output is true if and only if both of the inputs are true. So an example of this in plain English might be, if the key is in the ignition and my foot is on the gas, then the car moves forward, right? If the key is not in the ignition, but my foot is on the gas, still nothing happens. If my foot is on the gas, but the key is not in the ignition, still nothing happens. I need them both to be true. And so we can sort of represent that by this truth table here, showing the various possible permutations of our inputs, arbitrarily called A and B, just to keep them generic, and what would be output by this function, this AND function, which only outputs true if and only if both of the inputs are true. If either of them is true or neither of them, we get an output of false. And this pretty much snaps to our English language understanding of what the word AND means. It requires both of these things to be true. I just want to make sure we're on really firm theoretical footing so we can press ahead to more complicated things. That's kind of the theme of these, right? It's like, let me tell you about a thing you already know in a slightly more nerdy way, and then we'll build some stuff off of it. We also have our logical OR operation, right, which is true if our output is true if either of our inputs or both is true. So an example of this in plain English might be if I have eaten a turkey or I have eaten a hamburger, then I am full. If I've eaten both a turkey and a hamburger, I am still definitely full. The only case in which I'm not full is that I've eaten neither of my possible meals. There might be some other functionality where I'm sad and overfull and sick in there as well. But for the purposes of this logic example, right, the output is true if either of the inputs is true. If input A is I have eaten a turkey and input B is I have eaten a hamburger, if either or both is true, then the output I am full is true. Make sense? Cool. The NOT operator, really simple, inverts whatever comes into it, right? You put in a true, you get a false. You put in a false, you get a true. If I am alive, let's see, if the input is the state of me being alive and the output is am I dead, if I am alive, then I am dead is false. If I am not alive, if I am alive is false, then I am dead, right? And then here's one that's just a slightly bit more esoteric, but you may have seen it before, is this XOR, this exclusive OR property, which is true if either input is true, but not both. For example, if in my Pi shell I have apple pie, let's say my inputs are, in my Pi shell I have apple pie filling, and my other input is, in my Pi shell I have chocolate creme, and my output is, I have a delicious pie, right? If I have neither of my fillings, I do not have a delicious pie. If I only have chocolate creme in my pie filling, I have a delicious pie. If I only have apple pie filling, I have a delicious pie. But if I have apple pie filling and chocolate creme, I do not have a delicious pie. That's an example of an exclusive OR style operation, right? Where the output is true if one or the other of the inputs is true, but not both. Capiche? So we've been playing with these various ideas in our sort of if-then statements already, right? I kind of threw this in, I think, in like week 3 and just sort of rolled with it, but I think it's relatively approachable as a concept, right? We've seen this double ampersand, double bar, and exclamation point for our and, or, and not in our various situations. So we have statements like if millis is greater than 1,000 and it is not the case that the button reading is low, then trigger the rocket to launch or something like that. So we have this idea of and combining these two operations together and saying, hey, this is all only going to be true if both of these are true. We have this not, this negation, sort of inverting this reading here that is being taken. And we might have an example like down here, if the fire alarm in the bedroom variable is true, or the fire alarm in the kitchen variable is true, then, run the function call fire department, right? So if either of those fire alarms is going off or both, we need to take some action, right? This hopefully tracks through a little bit, right? This is sort of maps to the English language concepts of and, or, and not. We don't have a built-in logic symbol for exclusive or, but I will leave it as an exercise to the reader for how you could build that up just given and, or, and not, right? Questions so far? Feel free to shout them out, as always. A good fundamental basis. I'm going to roll ahead, but ask good questions. Please don't use Arduino as a fire alarm system. It's amazing how many weeks have involved fire, either through story or actually having fire here. Maybe a little bit troublesome, but here we are. So in tandem with our logical comparisons here, our logical functions, we also have in the Arduino, and really in the C++ programming environment, we have these bitwise functions that operate very similarly that we'll go into detail in a sec here. And I just want to show you that their symbols are similar but not identical. We have single ampersand for a bitwise and. We have a single vertical bar for a bitwise or. We have this tilde represents a bitwise not, and we get an exclusive or operation here. It's this caret. The bitwise operations operate on individual bits rather than truthiness or falsiness of a value. So let me show you what I mean by that. Let's look at the bitwise and operation. Works a lot like the logical and, right? The output is a 1 if and only if both of the inputs are a 1, right? If both of your input bits are 0, you get a 0 in the output. If either is a 1, you still get a 0 in the output. It's only if both of the input bits are a 1 that your output is a 1. So what that would look like is this. Bitwise logical functions always operate on individual bits of a byte or a longer variable. So let's say I was taking this arbitrary byte here of some ones and zeros, and I was doing a bitwise and with this other byte here that I just made up. And really, this probably would be more clear if I wrote this as not and, but ampersand. Make everything line up again. Right? When we bitwise and these together, the output is the individual result of the individual bits anded together. So look at this first bit here. We get a 1 and 0. Well, we know that's 0 because they both have to be 1. 1 and 1 is 1. 0 and 0 obviously is 0. 1 and 0 again, no, not good enough. 1 and 1 is 1. 0 and 0, 1 and 0, 0 and 1, all 0. So our result of taking the bitwise and of these two bytes that I made up is this variable down here, this byte down here, which has 1s only where both of the input variables have 1. I should say I write it in this format just to make it really easy to see where the various bits line up. This shouldn't be confused for addition, right? This line is just meant to say, like, here's the result down here. We're not adding or carrying. We're doing on each individual sort of vertical slice, each individual bit, we're taking an and that gives us our output logic down here. Sort of makes sense? I'll do a few more examples, but again, please feel free to jump in if something's feeling a bit strange, right? We have a bitwise OR function, much like our logical OR, same exact thing. If either of the input bits or both is a 1, then the output bit is a 1, and only if both of the input bits are 0 do we get a 0. So similarly, here's an example. If we were to take a bitwise OR of these two bytes, anywhere where there's a 1 or even two 1s in the inputs, we get a 1 in the output. So 0 or 0, still a 0, but this is a 1, these are both 1s, so that output value is a 1, this is a 1, this is a 0 because both of those input pairs are 0, 1, and 1. So we've gone bit by bit through our various inputs, applied that OR function to them, and that gives us our output. Cool. Similarly, we have a not function, our inverted function, which takes every bit of the input function and makes it a 0 if it was a 1 if it was a 0, sort of flips them 0 and 1. And we have our exclusive OR, right, which remember will output a 1 if either of the inputs is a 1 but not both. Right, this is either one or the other, but not both of these things. So 0 or 0 XOR 0 is 0, 1 XOR 1 is 0, and so on. And so to do a bonus example, we can see the output bits here are a 1 when either one of the input bits is a 1, but not if both of them are, right? So here's a 1 exclusive OR with a 1, the output is going to be a 0 in that case. Cool. So these things exactly map to our logical concepts. I just want to really hammer home the idea it's not adding, subtracting, there's no carrying. We just go bit by bit, place by place, and apply our given operation to. So, Jeff, as I hear you asking out there, as I feel like you may sometimes ask yourself on these Sunday nights or Monday nights, or especially as we get toward like, a Jeff class 90 minutes and a generous amount of change, why do I care? What is the point? I will show you. I swear there is a point. And it comes back to this question that we sort of started with of how do we set to 1, clear to 0, or flip a single bit in a byte, say for manipulating our port, where we don't want to be overriding values we don't need to. We just want to be sort of manipulating the bits in them. Let me go back to these tables and show you some interesting things. Let's look at our bitwise AND table here, right? And for the sake of this, I want to think of these not as two generic inputs anymore. I want to think of them as, say, our target byte, our given byte, our value that's already in, say, our port variable, and something we can apply to it to cause something to happen. Let's say that this first input we don't have any control over, it's a given, and I'm going to use a second input in a logical operation to do something to create the output that I want. Cool. So what I want to look at is a couple specific rows of this particular table, the bitwise AND function. Let me highlight a couple of them here, right? If we look at these two specific rows, we can say if we have a 0 in our initial byte and we AND it with a 0, we get a 0. If there's a 1 there and we AND it with a 0, we still get 0, right? So no matter what our initial byte was, if we AND it with a 0, we get a 0 for the output, right? So does that sort of make sense? In our initial byte here, we could have a 0 or a 1, but if our thing that's under our control is we AND it with a 0 is going to come out the other side no matter what the initial bit was. Looking at the other two rows of this table, right, if we were to AND something with a 1, right, a 0 becomes a 0 and a 1 becomes a 1. So in a certain sense, anything in our initial byte ANDed with a 1 doesn't change. Anything and a 0 becomes a 0. Anything and a 1 becomes a 1, because stays whatever it was. So in a certain way, this is how we're going to be clearing a bit, because now we have a way of setting some things to 0 and leaving other things unchanged. Let me show you what I mean. Let's say this is our initial byte. Again, I just made these. I made some 1 and 0, 1 and 0, 1 and 0. The actual values don't matter, but here's the demo, right? Let's say for whatever reason, I want to set these 3 bits to 0. I want to clear them. I want to make them 0. And I want to leave the other bits unchanged. I don't know what they are. I don't want to know what they are. I just won't want to change them. So given our rules from a moment ago, anything I want to clear, set to 0, I'm going to AND with a 0. Anything that I don't want to change is going to AND with 1. So what I'm going to apply is this byte here. Any position I want to clear, anything I want to 0 out has a 0 in that position. Anything I want to leave unchanged is going to have a 1 in that position, right? When I complete that operation, we can see if we go through our logical AND operation that we now know, right? 0 and 1 is 0, so 0 is unchanged. 1 and 1 is 1, unchanged. 0 and 1 is 0, unchanged. 1 and 0, aha, we've cleared that bit. It's now set to 0. 1 and 1, unchanged. 0 and 1 is 0, still good. 1 and 0 is 0. Ah, good, we cleared that bit too. And 0 and 0 is 0. We decided we would need to clear this bit. Maybe we didn't even check whether it was 0 to begin with, but we knew after this operation it better be zeroed out, so we ANDed it with a 0 to make it cleared. So this is how we're going to clear our bits. And we'll summarize all these rules at the end, because I know there's going to be a lot of words, a lot of face words coming out at you, but I hope this is sort of starting to click as how we can use these bitwise operations to affect certain bits within our bytes and not other bits, right? So that's how we're going to clear things. That's how we're going to zero things out. How are we going to set certain bits? How are we going to make sure that they're 1? Similarly, we can do something with the bitwise OR, right? Let me highlight a couple rows of this table. If we take a look at these couple of rows, if our initial byte is a 0 and we OR it with a 1, we know 0 or 1 is 1, because there's a 1 in there. 1 or 1 is 1. So anything ORed with a 1 becomes a 1. And similarly, 0, if we OR it with a 0, becomes a 0. 1 becomes a 1. So anything OR 0 doesn't change. Sort of the inverse of the situation we've just seen here. And this all just immediately follows from the definitions of AND or OR in these tables. So the rule of thumb, if we're setting a bit, is to to OR those places with a 1. Anything you don't want to change, you leave as a 0, right? So in this example, if I say I wanted to set these red bits to 1, and again, they might already be 0, they might already be 1, I don't want to know, I don't really care, I just want them to be 1 after I'm done with them. I'm going to set those positions in my sort of working byte here to 1, and when I OR them together, we'll see that those bits are set to 1. 1 or 1 is 1, 0 or 1 is 1, everything else is unchanged. The last functionality that I want to show you is how to toggle a bit, right? If it's a 1, make it a 0. If it's a 0, make it a 1. Or maybe I don't want to change some other bits there. So for that, we can use our bitwise exclusive OR. And similarly, I want to highlight a couple of rows in the table here, right? If I have in my target byte is a 0 and I exclusive OR it with a 1, I get a 1 out. So a 0 becomes a 1. In my initial byte, if I have a 1 and I exclusive OR it with a 1, I get a 0. So by exclusive ORing, with a 1, I flip my bit. So exclusive OR 0, exclusive OR 1 is 1, 1 becomes 0. And similarly, if I exclusive OR with 0, I get no change. 0 becomes 0, 1 becomes 1. So anything exclusive OR with 1 gets flipped. Anything exclusive OR with 0 doesn't change. So one more example, let's say I want to flip all 4 of these red bits here, and I don't want to touch the others. I'm going to exclusive OR that initial bit with a byte that has 1s in those positions and 0s everywhere else, right? And when I come out the other end, just as I work through my truth table, so 0 exclusive OR 1 is 1, 1 exclusive OR 0 is 1, it doesn't change, 0 becomes 1, 1 becomes 0, and so on, right? Just how the properties of the exclusive OR work. So to sum up those various rules, and I thank you for letting me take the time to talk your face. I was a math minor in college. I really love all talking about this math stuff, so thank you for allowing me to work through all the proof that this stuff works. But if you wanted to sort of cut to the cheese, here is the gist of it. To set a bit, to make sure that it ends up being a 1, you OR it with 1. To clear a bit, you AND it with 0. And to flip a bit, you exclusive OR it with 1. And the complements to all of these things will leave the other bits in your byte unchanged, right? So if you're setting some bits and leaving the rest alone, you would put 1s in the positions you wanted to set and 0s in the other positions, and so on. All right, let's turn this into proper reality, and I'll show you how this all works out, right? So our problem was down here in our if statement, where we were sort of clobbering the value of our port, where we'd really like to just be clearing and setting a bit of it. So rather than sort of doing this manually, what I'd rather like to say is port D, is that a decent size? I think it is. Rather than saying a hard value, I want to say port D is equal to port D, and we know, so reading is high, LED is low. So I'd like to be clearing bit 2, and we know to clear a bit, I AND that position with 0, and everything else stays a 1. So I'm going to do port D and binary 76543 76543 right? So I'm ANDing that position. I'm ANDing this whole previous value of the port with this binary, this byte here, which I know, because we just talked about how AND and OR and things work, I know that these ones aren't going to change any of the related values in this variable, but this is going to make sure that my result has a 0 in bit 2 of the output. Does that sort of make sense? I hope so. Chris says, how do you flip a bit a lot? You exclusive OR it over and over and over again. So similarly, like in this step down here, where I want to do a digital write high, I want to turn this LED on. I'm going to do port D equals port D or is good. Muted. What? Muted again? Hello? Testing? Oh man. So oh, you know what it is? The mute key that I have assigned is the / button, which is right below backspace. That's I thought that was going to be nice and out of the way, but it's not great, huh? All right. Well, thank you as always. I will I'll have to pick a different key for next week. Something, or maybe I'll put it on my X keys since it's a little bit further away from the system. So right, we said set the port D. Yeah, So I want to set this bit of port D to 1 in this output here, and I know I can do that by ORing port D with this binary value, right? The zeros, because I'm ORing, aren't going to affect any values. The 1 is going to set it. Oh, Nate, the foot pedal. I didn't look. I forgot to look. Thank you for the reminder. I'm pretty sure. So, like, you can't see, but, like, this is the pretty part of the shelves. The chaos is down below the camera where you can't see it. And I'm pretty sure the foot pedal is down in there, and I'm a little bit scared to go spelunking. But clearly, it'd be worthwhile. What I really want is a temporary mute that only mutes when I'm holding it down. There's probably a way to do that just with an OBS. But we won't do that now. We'll talk about Arduino stuff now. But that's a thought for the future. Right? So hopefully now, if I haven't made any typos, when I upload this code, we should be back to that original functionality where when I press the button, did I get my, no, LED is on 2. Let's see. Port D equals port D and port D equals port D or. No, that's correct. Here, I'm going to cheat a little bit just for the sake of time. Just peek ahead to what I wrote last time. Port D and port D or. No, that's right. Did I make a typo? That seems more likely. If reading equals high, port D is port D and 0. Port D equals port D or 1. No, that should be right. Maybe there's a wiring issue. Port D, that's 1, that's 2, that's LEDs on 2. Let's see. Port D, did I remember to set my pull-ups correctly? Let's find out. Port D, DD or D, pin mode LED pin 2 is an output. Pin mode LED pull-up is a 1. Port digital reading equals reading button if reading is high. If reading is low, port D or. No, that should be right. Maybe my flash just died. That would be a really ironic way to have this go. I have had this Arduino for I do not know how long. That would be a real bummer. It's interesting. So I do enough prep of these that I can be relatively confident. But you can see like later in my later examples, port D equals port D or, port D equals port D and. So I'm really reasonably confident that's right. Just did I screw up some setup here? You know what we'll do? We'll go back to the original example just with pin mode and reading and stuff, and if we'll make sure that this still works, and if it does, and it does, so it's a code issue, not a wiring issue. That's a good way to double check if your code has broken something or your hardware has broken something. Go back to the previous version of your code and see if that sort of unbreaks things, as it were. So what's happened here? What has gone on here? Port D with bin D and port D equals port D or that byte. Now that should be right. Let's see if I've screwed up something else here in my pin mode section. It's certainly possible. No. Let's see. What have I done wrong? I'm gonna take just a little bit of time to troubleshoot this because you're always like, oh, the troubleshooting is useful. Just to see some technique. Let's basically start undoing things. Right, so I'm gonna undo these port statements that was the whole point of the thing that I was really hoping would work and would show off how smart and clever I am. Right, so if I uncomment those, then things start working again. So clearly the issue is somewhere in my new code. Port D equals port D or binary. Seriously, that should be correct. Why is that not correct? Let me upload my later code. This is like the cake baked earlier example of this thing. So that works, right? Which is just based on this original code. So I'm guessing I have a typo in here somewhere. And if I can't find it, I will move on because I know that this works. But I mean, clearly it doesn't. So like, what have I missed? Let's see. Cheating by looking at myself in the future. Port B to Z, port B, port B. It's an input pull-up. 10 points to Gryffindor for anyone who spots it before I do. Digital read button. Button is high. Port D and... Here's here's another troubleshooting thing we can do. So I'm going to jump ahead to code that I was previously confident worked, right? Which has some things some shortcuts we haven't learned on yet. But I'm going to uncomment this, what I think is the exact same statement. Maybe something in the setup portion of my code is wrong. And I'm just not configuring this correctly. Let's see. Ah, yeah. So that does work. All right, so I'm just going to copy and paste these statements into my other code here, and we'll see if when I figured out what I'm doing wrong, I'll make sure I give a full explanation. So that's the same, and this is the same, right? So let's upload that. But again, so this should still in theory be broken. Oh, I see. I wasn't looking at the computer there. So something I'm not setting up something right is what's happening here. Come back to the computer. So reading, taking a reading, DDRD, digital read button. Do I have my button as an input pull-up? Sorry, y'all. This is an interesting one. I'm just not entirely sure what's happening. Pin D, DDRD equals. Have I dropped a 0 or a 1 somewhere is what I'm wondering. Like, is something not actually configuring right? Reading equals high. Do this. Otherwise, do that. No, that should be right. I'm so bewildered because that's the same thing as this code, which I wrote earlier. All right, we'll give myself just one more minute, and then I swear we'll move on. But I'm a little bit stymied because that is the correct syntax, as we can prove by it working over here. So what am I not setting up right? Maybe it's my port configuration. All right. This is the last thing I can think of to try, and then we'll move on. Binary. All right, upload that. Table. Still nothing. It's so bizarre. Well, you can. It's good that I muted myself there. Let's see. Do you have pin 5 or you need a pin 6? Maybe that's what I'm thinking. Is that I have a typo. I'm plugged into physical pin 5. This corresponds to digital pin. Let's see, 0, 1, 2. Oh, you're over here. Boop. Pin 2, 0, 1, 2, 3, 4, 5. Right. It's 2. Oh, LED. No, the LED's on pin 2. Port D or pin 2. Port D or with 1. So here's what I'll show you why I'm stymied myself, and then I swear we should move on. So this is the code I wrote earlier, and you'll see it's exactly the same. LED is 2, button is 5. DDRD equals this string, port B equals this string, so this pin 2 is an output, pin 5 is an input pull-up, reading is digital read button, if reading, guess I could do this, so you don't actually need to do digital read equals high, right? It's just the reading itself, as we know high is the same as true, and low is the same as false. We can just say if reading. But that shouldn't make a difference, and indeed it doesn't. Let's see. Port D and 0. Port 1. That's this statement. It's got to be something dumb. Digital read button. Digital read button. Well, you know what I will do then, just because I know that this code is working, although I can't see how it's different from the other code, I'm going to pick up working with this code. because it's working. Especially after a slash or something. Yeah, there's gonna be something dumb, and maybe at the end of the night we'll go back and figure out what it was. But what I'll do, this is why I can prepare these cakes in advance, so to speak, is that I can always jump to here if something goes awry. So the point I was making before this went so horribly off the rails, something in the else statement? I don't think so. So the digital write LED low, getting things back on track. Here we go. It's going to be great. Things aren't muted. We're having a great time. To set the LED to off, to digital write it to low, I want to set bit 2 to be a 0. I want to clear that bit, and I do it by ANDing the original value with a string that's all ones except a 0 in the place that I want to clear, because that's how you clear a bit. And if I want to turn it on, I want to OR it with a byte that's zeros everywhere except where I want to turn it on, because that's how you set a bit, is set it to 1. And when I upload this code that I just wrote in front of you like a pro, it's going to be great. When I come back over here, we say I have that same functionality. Extra space after slash in the program and the else between the thing and the parentheses. The problem there is an extra space, but I guess there's parentheses, but it shouldn't make a difference. All right, well, so this is, as far as I can tell, exactly the same code as I just wrote live, except that this one works. You could ignore this line for now. This is our next step. But you can see we take a reading, and if our reading is true, we turn that LED off. If it's false, we turn the LED on. It took us like 17 minutes to get from a bunch of slides to the conclusion, which didn't actually work, which I feel a little bit silly about, but that's all right. That's why we prepare these things in advance. Does that make sense? I guess with all that rambling, I'll say it again in case it didn't. To turn a bit off, we AND it with a byte that's all ones, except there's a 0 within the bit we want to turn off. To turn it on, we OR it with a byte that's a 1 in the position that we want to turn it on. So really, this statement, this OR statement, is the same as this digital write. We're just doing it directly at the port level. Cool? Yeah, we made it to Chris says we made it to 90 minutes. I knew we would. I knew there was gonna be a goof. That's gonna crush me that thing didn't work. It's bugging me that it's, well, that'll be the after stream. We can all go through and debug my code together. That sounds awful. All right, let us carry on. So you're not just staring at me, staring at my computer in the side. So we know how to set, clear, and flip bits. Neat. That was the point of that whole digression. Let's learn about a few more registers now that we can, in theory, we can do things with them. In this code, let me, which version am I working with now? This code can go away. This is the code I want to work with, and I'm going to save a new copy of it so I can find it later. So this byte here that is turning off this LED, and this one that's turning it on, and honestly these up here where I'm setting whether a pin is an input and an output, and it's whether it's got a pull up, these are perfectly functional. This is perfectly fine code, but these bytes are just a little bit unwieldy. Really what I want to encapsulate is the idea not of like that it's these 8 bytes, but this is encapsulating the idea of I want a 0 in position 2. Or I want a 1 in a position 1. I want this 1 in position 2 and zeros everywhere else. I want a 1 in position 2 here, and in position 5 here, and zeros everywhere else. There must be a slightly easier way to start encapsulating that. And to show you that there is, because otherwise why would I be talking about it? And to allow us to get to a place where we can start talking about inputs, I need to introduce one more operation that we can do on bits, which is the bit shift operator, which takes a byte or another number, but often we're working with bytes, and shifts it a number of bits to the left or to the right. So here's what that means. We have two operators. They're the double less than and double greater than symbols, essentially. They mean bit shift left and bit shift right as if they were arrows, right? The double less than symbol here, the leftward shift operator, says take my input number, my bit here, and shift it to the left by the number that follows, padding with zeros as you go. So in this case, this arbitrary byte, 0, 1, 1, 0, 0, 0, 0, 1, left shift 1, all those bits basically move one position to the left. So I get 1, 1, 0, 0, 0, 0, 0, 1, and I pad with a 0 here. So this 1 moved over a place, I had nothing to follow it, a 0 comes in to take its place, right? Similarly, I can shift a number to the right by a number of bits. So take this byte here, 0, 1, 1, 0, 0, 0, 0, 1, right shift by 2 moves all those bits 2 positions to the right. And it's being hidden by my Google Slides little menu there. But we can see that these two ones have moved 2 places to the right down here. Well, they're a little hidden, but they're moving 2 places to the right. If I do this, is that better? No, not really. This one at the end here has sort of fallen off the edge of the earth, and we had to pad with some zeros over here as we shifted things to the right. We can see sort of all the bits move a certain number of places to the left or to the right with these bit shift operators. So just to give you some examples, we, of course, have been writing out the full byte each time, but much like, just to type it out loud, much like the number 13 is the same as the number 00013 is the same thing as the number 00013. When we're writing things in English, we don't usually put, like, extra padded zeros at the front, but we certainly could. In the same way, these binary numbers, it's useful to write out all the leading zeros. It sort of clarifies that we have 8 positions that we care about, but we could just as simply, we could have written this without the leading zeros. This means the same number, we're just not adding the zeros in the front of it, right? So, in the same way, I want to take a little look at bit shifting just the number 1. If I take just the number 1 and bit shifted, well, if I bit shifted by 0 places, it doesn't change. That's just a 1. A binary 1 is a 1 is a 1. So that would be 000000001, right? If I were to bit shift the number 1 over to the left shift that number by 1 place, I'd have, the digit 1 shifted over by 1 place. If I had it shifted to the left by 2 places, I'd have the number 2. Not the number 2, I'd have the number 000000100, which is a 1 in the second place. If I shift it over 3 places, I have a 1 in the third place, and so on up to 7 places for my byte. I have a 1 in the 7th place. And what I want to point out here is that this is a really easy and sort of straightforward way of creating a number which has a 1 in a specific position of our byte, which is often more what we care about than sort of the number that the byte represents. And in some sense, if I need a number, and we'll do this in the code in a second here, I need a number with a 1 in the second place. I could write it out as this B000000100, or I could write it as 1 left shift 2. And though I know that we've talked about a lot of different terminology and symbols tonight, when you start getting more comfortable with this 1 left shift 2 operation here really will start to click in your mind as a byte with a digit 1 in the second place, in the third place, in the 0th place, in the 7th place, and so on. It's just a little bit more visually parsable than a long string of zeros and ones where you have to count, like as I was sort of doing in troubleshooting, right? I had to count where the zeros were and the ones were, and did I do it all right? I'd rather just write things like, hey, I want a 1 in the third place, and I know 1 left shifted 3 places will do that. So let's put that into our code. So rather than writing ddrd equals this thing, I'm going to comment that out. And again, if this breaks too, I have more cakes on the oven pre-made, so to speak. But instead of writing this binary string, I would say ddrd equals 1 left shift 2. And for port D, instead of that string, I want a 1 in the 5th place to go along with my button. I would say port D equals 1 left shift 5. Now, just because I'm being extra cautious, let's upload that. Just make sure that everything still works. Oops, did I make a typo? Function. Oh, something is compiling strange. Function definition is not allowed before. Why? Why, code? Why? Error 29, end of input. All right. Oh, is it because I have an extra space there? Is that the whole reason? Was the extra space before loop? No. Port D. Do I have an extra curly brace somewhere? Somewhere something is being defined as a function that shouldn't be. That's what that error message is telling me. Oh, we're right back at this. This is killing me. Because this code was compiling a moment ago. Oh, we're crashing and burning more than we usually do. Because does this compile? No, this is what we just ran, and it's not compiling. Why is it thinking that? Line 16, a function definition is not allowed in function. Oh, I'm missing a curly brace. That's what's happened. Yes, now that compiles. There we go. Whew! Ooh, I thought we were going to be 0 for 2. All right, I was missing a curly brace in my setup function. That's quite good. All right, so we'll upload that code. Yes, Chris got it before I did. Thank you, Chris. Yes, you spotted the curly brace error. So in theory, yes. So there we go. So our LED is still on when we press the button down, and off when we unpress, release. Release is the word I'm looking for when we release the button, right? So, and in some sense, like, I know this is extra symbology to have to keep track of, but I personally think, once you start to get comfortable with it, this is more parsable than this. And certainly if we were working in a 16-bit system, which we're not, but working with, you can do all these same things with 16-bit numbers and 32-bit numbers, right? Saying something like, if I had a port that had 16 bits in it, saying, these bits are going to be outputs is not particularly clear. I'd much rather have it in a form factor that just shows me which bits are ones and which bits are zeros, right? And I can do the same thing down in my digital write function down here. Instead of doing this string, I could say port D equals port D or 1 left shift 2, right? It has a 1 in that second position. Now here, I don't need exactly the same thing. I need a string that's not a 1 in the second position. I need a 0 there and 1 everywhere else. And thankfully, we have a little function to help us out with that. We have our old friend, the not operator, which inverts a binary bit, right? So this in here, 1 left shift 2, is all zeros with a 1 in the second place. Then I invert it, so I have all ones with a 0 in the second place, right? So again, upload that, make sure I haven't goofed again. See Nate's question. Do you have a pin 5 or you need a pin 6? I don't think so. Everything should be on pin 5. It's a good question, though. And since this code is now working, I'm going to roll with it for now, but we'll come back to troubleshooting whatever that was going on with that other one still. Not that question. Oh. Nate, that's the last question I see from you. Nate, I see muted. Do you, I might not be in the live chat. That'd be a shame. Why would it never, wow, that's unfortunate. Thank you for pointing that out. Yes, now I see all the things. Let's see, 1 left shift 8 equals, so, does 1 left shift 8 equal binary 0? It depends, in what context your number is being used, and I'll show you what I mean just by typing it out. In a context like byte B equals 1 left shift 8, yes, binary, a 1 shifted over 8 times is going to be 0. Now, if I have something like int I equals 1 left shift 8, that's going to be equal to 256, if I've got my math right, 2 to the 8th. Because an integer, right, takes up more than 1 byte, right? So I start with the number 1, I shift it over 8 times, and I end up with a number that doesn't overflow and remains in a valid number. In fact, if you have a long, say long L equals 1 left shift, you could do long left shift 17, right, and still have that be a valid number because longs take 4 bytes, so have up to 32 possible bits in them. But in the context of a byte, and when we're working with these port numbers, the assignment is sort of taken to be a byte or interpreted as a byte when you assign it to a port. Yeah, left shifting it over by 8 bits. We'll cause it to roll back over to 0. Nate, that's so interesting that it like weirdly. I was in top chat mode rather than live chat mode. It like that's like the one thing it swallowed. I wonder if YouTube thought that like something was like hackery or spammy or vulgar about the 1 left shift 8 equals something message. Maybe it was like that's a robot. I'm gonna hide him. That's so weird. Well, you learn. I mean, we're 17 weeks in, and I'm still learning things about how YouTube goes, which is also kind of fun. So, Chris, thank you for flagging that, and I'm now in live chat. So I guess we'll find out more things. Where were we? So this is just a little shorthand for you to know when you're working with these binary bits and bytes. And I promised that it was going to allow us to start working with input as well. And to do that, I need to introduce one more register. Oh, look at this nice slide where I showed a little bit about inversion, right? So we had our string here, 1 left shifted by 0 times has a 1 in the 0th place. If we invert that, we get a 0 in the 0th place and 1s everywhere else. and the pattern continues, right? This is what I sort of described in the code there. But this is a really easy way to form a string that we sometimes need, which is ones everywhere and then a 0 in a specific place. Yeah, now we can see all the comments. Yeah, now I'm in strict mode. Now I'm going to see all the sneaky things you've been trying to ghost past by putting them in form of numbers and equations, you nerds. So does this make sense as well, right? We sort of form a string and then we invert it to give ourselves a 0 in the place that we need. Again, I know it's like a little bit of a cumbersome notation when you're just getting started out with it, but you know, once you start getting used to this notation, and you'll see this a lot if you're working in libraries that manipulate ports or various things, you know, rather than saying, hey, set this port to this byte, set it to the inverse of 1 left shift 3, and your head will just go, oh, okay, so that's going to have a 0 in the third place. It must be doing something with it. You know, it's funny, Nate, I made a pre-stream checklist at one point, and I haven't updated it since like week 4. And there's clearly some things like live chat that I didn't know about. There's also things now that I do that I didn't have to do back then. I was like, oh, I'll remember. Nah, I should update the checklist. It's things like turn the lights on, plug the USB cameras in, move the chat windows where I want them, all that kind of stuff. But mic unmuted, yeah, that one needs to be like on a post-it on my forehead, so I don't mess it up in the middle of the stream. So let's see, when do I introduce the? Hang on, I'm gonna peek ahead in my slides because this is not quite the. Oh, okay. Yes, actually, I've got one more shortcut to show you before we talk about input. So. This notation, this 1 left shift to the left by a certain number of places is all well and good, but the C++ environment at AVR-GCC provides one more little shortcut for us, which is this thing, this underscore BV. It's a macro. We can think of it as a function, and that just means 1 left shifted by, say, X position of places. So, say, you know, BV4 is 1 left shift 4 is a 1 in the 4th place. BV stands for bit value, and so you can read this, you know, underscore BV of 4 is you know, the bit value of 4 of 1 in the 4th position of that byte. You could do BV of 7, BV of 0, or so on. It's the same way of formulating these useful bytes with a 1 in a specific place. And much like before, we can take the inversion of them to get a number with a 0 in a specific place. So in not BV that's a typo, not BV2. Get back here. Not BV2 is a byte with a 0 just in the 2nd place. And again, this is the notation that will kind of become more familiar. It's like, oh, BV4, so there's a 1 in the 4th place. Not BV2, there's a 0 in the 2nd place. And that will all start to feel a little more familiar and make things just a little bit more readable. So let's go into our code and we'll make those adjustments, and then we'll talk about input. So up here, rather than saying 1 left shifts 2, I can say DDRD equals bit value of 2, right? Down here, rather than saying port D is 1 left shift 5, I can say BV of 5. All right, I'm gonna upload that real quick, just because I'm a little bit gun shy now. Like after our little goofsala earlier, I'm a little bit nervous. We'll come down here and say port D. Let's copy and paste this. Port D equals port D and not B underscore BV2, and port D equals port D or underscore BV2, right? And this, I think, again, the notation will take some getting used to, but I think this is even more readable than this, right? Or than our sort of, you know, long binary strings that we were working with earlier, right? Port D, and I know OR is the thing we use to turn bits on, right, to set bits. So OR BV2, so I'm turning on bit 2 in port D. Up here, oh, I know and turns things off. I'm turning off bit 2 in port D, right? This sort of starts to become a little more visually apparent. Let's upload that and just double check that it works, because apparently things are just not always going to plan tonight. Yes, it does work. That's great. And now I can talk to you about input using ports. Oh, actually, I think I have 2 more slides first. Oh my God. No. Here we go. Let's move on. Let's get to input, and I'll come back to short bit names because I wanna get you to these input steps. Here's how you do input with registers. There is a register called the pin register, the input pin register, and much like the other registers we've seen, there's a pin B, a pin C, and a pin D for ports B, C, and D. It holds the input value that a pin that's configured as an input is returning, essentially. So if pin 0 is configured as an input, if you read the value of that bit, it will tell you whether that input is high or low. If it's high, you'll get a 1 back. If it's low, you'll get a 0 back. Same for all the other pins there, if that sort of makes sense. So how are we going to turn that into something we can work with in our if function? So really what I'd like, and this is the snippet of my code, that int reading equals digital read button. I want this variable called reading. I want it to be a 1 if the button pin is high, and 0 if it's a low, right? That's what digital read button means, right? That's what our result is going to be. So we want to replicate that using some of this register reading that we can now do, right? So what I'm going to do, and I'm going to just do this, I think that's the summary slide, but I think it'll be clearer if I do it here. So let's comment out that digital read. Actually, that's where we're going to end up, so we'll get rid of that there. So if I were to just take pin D as an input, what I get back, right? So not pin D0, pin D, whatever, right? What I get back from pin D is a byte with 0s and 1s representing the input state of those 8 pins on port D, right? So in our case, let's say that the input is high. So on pin 2, right? Buttons on pin 5. So if that button pin is high, I would get back something like 0, 0, 1, 0, 0, 0, 0, 0, right? Bit 5 here is high because in this case I'm assuming the button pin is high for the sake of working through our example, right? What I want to end up with is just the number 1, right? I want my reading variable to be 1 because 1, as we know, represents true. So how am I going to get this 1 over to basically this position here to represent just the number 1? Well, I'm going to right shift it by 5, right? So I could say, have a quantity that I'm going to manipulate. It's going to be pin D, right shift 5, 5 being the position of this. I'm going to move it over 1, 2, 3, 4, 5 places so it lands here. But what if my readings from, say, digital pins 6 and 7 were also high, right? I could end up with a number like B 0, 0, 0, 0, 0, 1, 1, 1, right? Even after a left shift. If my reading was, say, 1, 1, 1, 0, 0, 0, and so on, I don't really care about these upper bits. What I want to know for the sake of this is, what is my button doing that's attached to pin 5, right? So what I want to do before I apply this right shift to move this bit over where I need it is basically zero out all of the other positions in this byte. So I'm only looking at this one little bit that I'm working with. And thankfully, we know how to zero out positions in a byte. We AND them with 0. So really what I'd like to be looking at is pin D and we'll do this in a few steps, right? And binary 0, 0, 1, 0, 0, 0, 0, 0, right? So this quantity is going to be entirely zeros if this position in pin D is 0. If it's a 1, it will remain a 1 because anything and 1 is unchanged. Everything else gets zeroed out, right? So I'm going to take pin D and this quantity, and then right shift it by 5. And we'll see, hey, it lines up with that thing that I wrote earlier. That's pretty cool, right? So if the 5th bit of pin D is a 1, I get a 1. If the 5th bit of pin D is a 0, I get a 0. And so this is going to be the new value of our variable that we're calling reading. So let's upload this to make sure it works because that's sort of the theme of the night, and then I'll go through that one more time all together. Oops, typo. Oh, didn't have a semicolon. Uploading, and we'll see everything still works. So we're getting that input like we meant to. So just to go through that logic one more time for working with specific inputs, right? So let's say pin D is something, because pin D, remember, represents the input state of all 8 pins connected to port D, right? So it could be, some combinations of 0s and 1s, but this green number here, this 1, is the variable the value that I care about, right? I want to know is that a 0 or a 1? Is it low or high? Because that's where the button is attached. So the first thing I'm going to do is zero out all of the other bits that are that are in this byte. I'm going to AND it with this value here that only has a 1 in the place I care about. That gets rid of all of my other 1s that might be floating around. Then I move that digit all the way to the end, right? So I either have a 1 remaining there or a 0, a true or a false, as we know. And this logic, right, is the same whether that reading is a 1 or a 0. Right? Now, of course, as we know, we could write this in a slightly more condensed way. Where's my thing? Right? So rather than saying reading pin D and this binary string, we now know about the BV macro, which has, it's just a slightly condensed form of that. This should work exactly the same way. BV and 5, right shift 5, and so on. Right? And if I come to the table, it still works. Cool. So one more way of making this even clearer about what's going on. I feel, so like, I think this is the right way to understand these topics in, but I totally understand, like, as I'm saying it out loud, we sort of started at the basest level and kind of the densest and harder to understand, and now I'm going to we're layering in all these ways to like make the writing of it clearer. So you wouldn't necessarily be writing like B00100101 in your code, but I think you do have to understand what's going on under the hood before we explain the clearer version. So sorry if it feels like I'm pulling the rug. I guess the metaphor would be putting the rug back under you as we come up with like better ways to write these things, but I think it is important to know what's going on under the hood of all these macros, so to speak. The one thing that I want to do to make it even more clear what's going on in some of these functions is to share with you the short bit names that are associated with each of the bits in these bytes. So going way back to the beginning where we looked at this little snippet from the data sheet where we said, you know, port D, for example, is called port D and has these various bits, and each of those bits has a name. Port D0, port D1, port D2, and so on. These really just represent the numbers 0, 1, 2, 3, 4, and 5. You can use them in place of 0, 1, 2, 3, 4, 5, etc. in your bit shifts, in your BV macros, and so on. So rather than writing, for example, which code am I working in? Here we are. Reading equals pin D and bit value of 5. I could say equals bit value of port D5. And I could also right shift by the value of port D5. And this now I think is the clearest version we've come up with so far, which says, hey, I'm looking at pin D5 and I want to get its value, I want to slide it to the right by that same amount, and that's going to line up with the fact that we're still looking at pin D5 on our Arduino here because that's where the button is attached. By getting the port D5 moniker into the code there, we sort of start to give people who are reading our code, which might be us in the future in a couple years when we've forgotten what we were doing with this darn project, a little bit more clue about what the code is actually doing. So you can use these numbers, port D0, port D1. All of the ports have this same structure. Well, I'm not going to scroll all the way back, but let me show you. If we go back to some of our port examples we were looking at, here's the data direction port, right? Where the bits are called DDD0, DDD1, DDD2, and so on. And by using those in your code, you would start to give someone else a little bit of a clue as to what your numbers were doing. It's especially helpful for control bytes that like all the bits may not be directly related, right? So if you were setting the value of the BODSE bit in MCUCR, you could do, I'll show you, you could do MCUCR or that, or you could write MCUCR equals MCUCR Hi! Jesus. Hang on. All right. Hang on one sec. I'm going to disable this mute button because it's been great, but it's also been far more trouble than it's worth. So I will just briefly go into my settings and delete. Ooh, I have a push to mute functionality. Let's apply that. If I do that, no, that's not working at all. Oh, thank you for push to mute. I don't know. All right, we'll just let that go for now. With muting and unmuting while yeah, that's fine. It was a good try. I'm killing the mute function now, so hopefully if I hit that button, yeah, nothing happens. Oh, goodness gracious. Thank you, everyone. Thanks for bearing with as you type BODSE. Okay, so the gist of the point with the BODSE where was this and this, right, which are some configuration functions deep in the Arduino, right? They do the same thing, but this second line here is, I think, clearer by a country mile than this, because we're sort of incorporating the meaning of this byte directly into our code, right? For our other example, right, where you're saying, you know, port D equals something like this, all relatively clear. But especially where the bits start to not have anything to do with their neighbors, using that BV macro is really helpful. Now, Chris, you had a question. So what happens when you have multiple buttons and LEDs when you're shifting things around versus a single setup like your example? Good question. Let me see how many slides we have left. I think we can just jump right to that example, and I can show you what will happen. What have we not talked about yet tonight? Short bit names, input register. Pin change interrupts is the last. This is like the last thing, and I got a couple more little tidbits to share. But yeah, let's do another example. Let me get out another button and another LED because they're right here. I don't even have to get out TummyCam to make that happen. So you're in luck. So let's come down here, and I'm gonna need we'll need to make up some functionality for this second button and second LED. So they may be like, I think like a single button that turns both LEDs on and off is not great. Like maybe one button turns on and off the red LED and the other button flips them both or something. Figure out some way to like make this tractable. I think that's a decent example. I'm gonna plug in my second button there. I'm gonna plug in that button to pin, let's say pin 1. And I'm going to tie the other end of that button to ground, and I'll make that an input pull-up in a second here. Ooh, that's the world's longest wire for this example, but that's fine. There we go. I guess I can zoom out just a little bit, because things are actually happening now. I'm also seeing I changed what kind of arm that this here camera is in, and I can see it's bouncing a whole heck of a lot here. So I think that's a no-go, as they say in somewhere that they have that accent. And we'll add another LED here. Let's add a green LED just to keep things a little bit separated. So I'll do green LED. Let's see, I'll need another little bit of wire here. Let's say green LED goes onto pin, let's do pin 13. We'll need a resistor. Do I have, that is a 2 ohm resistor. That won't do. Let's see what value of resistor this is. You need to print a different camera arm. You know, it's funny, Chris, both of the little like face cameras are on 3D printed camera arms. They're just not quite stout enough to like support a DSLR, unfortunately. Let's see, that is a 220 ohm. That should be fine. I guess I could have read the labels, but I'm a lazy person. I just had a multimeter handy. All right, I'll do my due diligence. We'll unplug the Arduino, and we'll plug in this resistor between the cathode of the LED and ground. All right, so now I have 2 buttons and 2 LEDs, and through the magic of Sharpies, let's color one of these buttons so we have a little distinction. So our original button will be gray, our new button will be our blue button, so we can see what's happening here. All right, so let's come over to the computer and we'll write some new code. Actually, I'm not using these constants here anymore, which is fine. So let's see. So what do we need to do? So we need to set up our LEDs as outputs here, and our LEDs, let's keep those LEDs on the same port, just to make this a little clearer that how they're interacting with each other. So rather than being on pin 13, I'm going to be on pin 7. So my LEDs are on pins 5 and 7. My buttons are on pins 1 and 2. So coming over here, so I need to have pins Let's see. My LEDs are... Oh, my LEDs are on 1 and 2? No, my LEDs are on... Oh, this poor wiring. This LED is on pin 2. The other LED is on pin 7. So what I need, just to show the long version first, I need DDRD to end up with a 1 in position 7 and 2. So 7, 6, 5, 4, 3, 2, 0, 1. Right? That's what I need my string to end up as. So bit 7 is a 1, bit 2 is a 1 because my LEDs are in pins 2 and 7, which are port D pins 2 and 7 in this case, right? So this is a perfectly fine way to write it, but I could also write this as DDRD equals BV7 or BV2. Right? So this is a 1 only in the 7th place. This is a 1 only in the 2nd place. If I OR them together, I'll have 1s in the 2nd and the 7th place. That's going to enable our two LEDs as outputs, right? I also going to want to enable pull-ups on both of our input buttons, and those buttons are on pins 5 and 1. So similarly down here, I can say this is going to be BV of 1 or BV5, right? So this is a 1 in position 1. This is a 1 in position, position 5. I OR them together. I have 1s in positions 1 and 5. Just make sure that compiles. Yep, looks like it does. So now let's see. So I'm going to need to take let's take the readings of both buttons. We'll do it port-wise. So my other button's on pin 1. And let's see, that first button, we'll call it reading gray for my gray button here. And I'll say my reading blue for my blue button. And we haven't quite figured out what we're going to do with them yet, right? But it's on the same port. I'm going to say pin D and BV port D1, right shift port D1. Right? So this is the entire byte that has all of the readings from that whole port on it. This only has a 1 in the first position. So if this has a 1 in that position, they're going to get 0, 0, 0, 0, 1. If not, it's going to be all zeros. Then I'm going to shift it over a little bit so that 1 or 0 ends up in the rightmost place. So my total value is either 1 if there's a 1 there, or 0 if there's a 0 there, if that sort of makes sense, right? So far, that's how these things are interacting, to your question, Chris. Like, I'm ORing some values together to create a larger byte that's going to sort of do the dirty work for us. Now, let's modify our function here. Let's say if reading gray, and reading blue, so if we're pressing both buttons, then let's set the value of the port. Let's say in that case, let's do this. Let's create a situation if maybe this is some kind of the worst missile nuclear silo you could ever have. If both buttons are pressed, we're going to launch the missile, and the green LED will turn on. If a rogue commander shows up and only one of the buttons is pressed, we're not launching the missile. In fact, we want to throw an error signal, and the red LED will turn on. And if neither of the buttons are pressed, the system is just waiting, and neither of the LEDs are on. So let's write that into code. So first, let's handle the case where both the buttons are pressed. So we want, let's see. You know what I want? So the only thing about that is it's kind of saying that the button state is directly related to the code. Let me propose a slightly different storytelling scenario, because I think it's going to give us a little bit more of an ability to demonstrate how these operations change bits without sort of setting the whole thing. Let me do a little bit more storytelling. Let's say that the gray button is the master key to our suite of hotel rooms that we're all staying at, because it's now 2023 and conferences are okay, and we're all staying in a great big hotel at the Electronics Bash conference all together, right? The gray button is our master key, and when that button is depressed and held, only when it's down, both of these lights will turn on. Let's see, when that button is down, both of these lights will be set to on. The blue button is just my room. I've got a purple shirt, but let's say it's purpley blue. When I press the blue button, it's going to toggle the state of the red LED on or off. So the gray button will turn all the LEDs on, unlock all the rooms. The blue button will allow me to turn the red LED only on or off, I think is the way to do this. So what I want to say is, if the gray button is not, let's see, if the gray button is low, in other words, if the gray button is 0, so this is only going to be true if reading gray is 0, then I want to set the state of both of those LEDs to on. So in that case, I'm just going to do a straight up set of the positions of those two LEDs, which we said were what, 7 and 2. The port D equals, say port D equals port D or BV7 or BV2. Right? Which is the same as saying this second quantity here is port D or binary 1 0 0 0 0 0 1 0 0. I think that's too many zeros, right? So I'm going to OR it with these two positions. So I'm going to make sure those two positions are on in my output, and this is just shorthand for them to combine those two things together, right? So that if my gray button is pressed, that's what I want to happen. Let's see, if the blue button is pressed, so if the blue button is low, so I need to invert that. If the blue button is low, then port D, now we're going to have a little bit of a problem here, equals port D exclusive OR, right, because I want to be toggling something, or just the value of the red LED, which is on pin 2, or BV2. Right? Now the problem with this, of course, is that this is going to execute as long as the blue button is held down. It's going to toggle it back and forth. So really what I want is some way to hold the state of this second button. But let me modify my storytelling a little bit. This is probably why I come up with these examples ahead of time, is to try and get the storytelling clear. But let's just modify the story. This blue, so if the president has come along and a president of the hotel has come along and unlocked all the rooms, the only thing I can do is stick my key in the lock and manually lock my room as long as I hold that button down, right? So in this case, instead of toggling it, I'm just going to say I'm going to temporarily shut it down by doing a port D and not BV2. So that's the same thing as saying port D and not, I guess port D and 1 1 1 1 1 1 0 1 1. Right? So again, anding with all ones, mostly unchanged, but in this position, I'm going to make sure that output is a 0. Now I can, of course, that's the same as inverting binary 0 0 0 0 0 1 0 0, right? Which is the same as this BV2. Does that sort of make sense? I know this is a lot of terminology so far. How are people holding up? This is one of those moments where like it's a good class, but I'm like looking out to the crowd and being like, are people following along? Are they dying out there? Are they just ready to like get to like the punchline where we start doing stuff a little more advanced with it? It's super good stuff, and like that's all of next week is applications, right? Is talking about more interrupts and stuff. So there is that coming. Just a little temperature check. How are things going on? Michael Glass asking a great question. Why would you want to manipulate registers rather than just using pin mode, digital write, etc.? Great, excellent question. Let me show you a couple of reasons why. Chris, I didn't quite finish your example, so let me put just a quick pin in that question, and I'll show you why you'd want to do some of these things. I think if I upload this, it may actually just work, which would be great. Oop, error. Don't give me an error. An error. Oh, well, there's your error. That would do it. Yeah, this is a pretty intense, like, mathy conversation for sure. So if I press the gray button, both those lights turn on. When I press and hold the blue button, the red light turns off. When the president comes back, he can enable them both. The blue button turns off. Notice that this blue button is not affecting the green button at all. If I reset, so everything goes back to 0, right? Everything starts off. It's just that this gray button is setting things to on to start with. In fact, we could double check that that's true by initially saying, yeah, so port D is being set to off initially. Reset that, come back to the table, right? The gray button sets things to be on, and the blue button should toggle the red if I don't have a wiring error there. Yeah, Palmer, I agree. It's a pretty dense one, and I maybe dove in a little fast to this example of like multiplexing interrupts. The gist of it, Chris, is that by yeah, slowly losing focus. Yeah, I'll cut to the chase. The gist of it, to answer your question, Chris, without reworking the whole demo again, is that the whole reason for doing these OR and exclusive OR operations is that you are only changing specific bits and not other ones. That's why instead of just like setting a port to be something, we OR it with a value, we AND it with a value, so that we're only manipulating specific bits within that byte. So that's the short answer. I guess I could have just said that. So jumping back to like why to the very good question of why do we care? Why would you do this? Well, actually here there's a really easy thing for me to show you. Let me go back to that very first bit of code, right? And if I hit compile here, we'll say that this bit of code takes up 902 bytes of program storage space. Not a huge amount, less than 2% of our program storage, but like a non-trivial amount for a program that basically looks at a button and turns on an LED. If I compile this last bit of code that we wrote for the Chris Wick example, even though it's doing significantly more, it's only taking up 484 bytes of program space. So one of the reasons you would do things in registers is that by condensing your operations into register-specific operations, you are eliminating the need for the compiler to have basically all of the functionality underneath digital write just to manipulate a single LED or function. So this digital write function, basically under the hood, is doing a lot of this like port manipulation for us, but it has to know about what the different ports are, what input and output state they're in, know which bits it can and can't toggle, whereas we're handling them directly. The code inside of the Arduino doesn't need to include any of that, so we can save some space. You can also save a little bit of time. Not necessarily coding time, but processing time. So when you call digital write or something like that, right, especially with a dynamic choice of pin or output level, it has to do a fair amount of figuring out again, like, okay, what state is the pin at now? When they say digital pin 8, what port, what pin is that, and so on. And so if you were doing a piece of code like, very simply, if the whole loop was digital write, LED high, digital write, LED low, right? Let's say that was our whole loop, just turning things on and off as fast as we could. That will be significantly slower than doing the port equivalent operation where you're toggling a specific bit in a byte. You can also, if you're doing portwise math, right, this is the digital write command is only ever going to turn a single pin on or off with a single command. With portwise operations, you can do up to 8 manipulations at a single time, which may be useful if you're in really timing critical situations. One of them might be if you're working within those interrupt service routines we talked about, and you really want to make sure that whatever you're doing inside that routine is operating as fast as possible. Condensing a bunch of, say, digital writes or digital reads into a single operation can be really useful. A common way of using an external interrupt is to say, when something changes, take a quick snapshot of a bunch of pins, and then later I'm going to figure out, if that meant a button was pressed or multiple buttons or so on, right? If you had to do a digital read of 8 or 10 or 12 different pins, it will take, milliseconds, but a significant amount of time in processing terms, when you could do, say, 1 or 2 port operations to take that whole byte of input and copy it somewhere else, and that would just be faster. So storage space, speed are reasons. There are also some things inside of the Arduino programming environment that you can only really do by manipulating registers, and that's where well, let me show you some examples now, and that will be the entire focus of next week. So to give you some examples of things, some more registers that exist and things you can do with them, right? We talked about the port, DDR, and pin registers that we've seen. The UDR register is interesting. That is the data literally coming in and out of your serial port that you can sort of access in a byte-by-byte direct way. The serial port also has configuration registers, much like the DDR port is basically a configuration register for your pins. You have this UCSR A, B, and C registers, configure various parameters about your serial port. You could also read from those registers to determine some properties of your serial port. Let's say you had a dynamic device that was for debugging. I'm thinking of like the dimmer racks that we used to have in our theaters of various generations. Some have a very fast serial port, some have a very slow one. So you could make a device that sort of plugs into one of these things and tries out various serial speeds and sells something bytes, right? There's not necessarily a built-in way within the Arduino to determine what your serial speed is, only to tell it to be something specific, unless you read from that configuration byte in memory, and that says, if the value is 1101, that's this speed. If it's 1110, it's this speed. You could figure it out that way. There's a lot of registers that have to do with configuring timers, and I know it's a bit of a tease, but that's our subject for next week. Pin change interrupts, though, we can talk about this week, and that will be a good place to close, because I know with all of the numbers and bytes and bits and math, it's probably condensing a little bit in people's heads. But let's look a little bit as to how you would configure pin change interrupts using this register math that we know now. Because I said last week, and it's true, you really can't configure them without knowing how to do this stuff. So let me show you what you would do. Here's a practical application. Only 2 hours and 15 minutes in. Here's a practical application. It's a fair question. So here's one register that's really relevant to pin change interrupts. And again, quick reminder, pin change interrupt, right, is a command to jump to a specific place in your code, right, into your interrupt service routine, whenever one of a specific set of pins changes from low to high or high to low. And with these PC interrupts, these pin change interrupts, we don't get to know whether it's going high or going low, just whenever it changes, right? So here's one of the registers that's relevant to us. The PCICR, the pin change interrupt control register, only has 3 relevant bits, and if any of them are 1, they turn on pin change interrupts for a specific port. So pin change interrupt 0 relates to port B, digital pins 8 through 13. Pin change interrupt 1 relates to the analog pins, and pin change interrupt 2 relates to the digital pins. D0 through D1. We also have a PC mask, a mask register, that allows us to select which of the pins in that port are going to point us to that interrupt, right? So though interrupt 2 is connected to these 8 digital pins, D0 through D7, we can mask some of them out and say, hey, I don't care about pin 0, 1, 2, 4, 5, 6, or 7. I really only want to listen to pin 3. So we could set the corresponding bits of the pin change mask register, and we have mask registers for interrupts 0, 1, and 2, so PC mask 0, PC mask 1, PC mask 2. Any position with a 1 in it is going to trigger our interrupt on that pin. Any position with a 0 is not going to trigger an interrupt on that pin, right? So let's look at a bit of code using that. And this, if you're following along at home, let's see, do I still have it open? I do. This is the pin change example from the website to play along with at home. It's using all of the things we have tonight to set up a pin change interrupt to toggle to basically do the same thing we've done all night, but with a pin change interrupt. So I've got a button that's going to be on pin 5, port D5, an LED on port D2. I'm going to configure my LED as output, right? So my direction register needs to have a 1 in the position corresponding to the LED, so it's going to be this bit value LED. My button is going to need to have a pull-up on it, so I'm as a BV button, so there's a 1 in the position corresponding to that button, because for an input, that means there's a pull-up, right? I've wrapped these 2 commands where I'm configuring my pin change interrupt variables in this CLI SEI. We talked about this last time, but just a reminder, this CLI is the same thing as disable interrupts. I think actually it's just called no interrupts in Arduino land. An SEI is the same as the command interrupts. It's generally good practice if you're configuring other interrupts to turn off interrupts in the meantime. You wouldn't want to get into a situation where you're in the middle of configuring a new interrupt and have an old interrupt you. This is just good general practice. Not strictly speaking necessary in a really simple example like this, but turn interrupts off, and then I'm going to configure my interrupt register. I'm going to turn on pin change interrupt 2 by setting that bit, PCIe 2, which you'll remember right? PCIe2, this bit here, this second bit is going to be set to 1 to enable that pin change interrupt, right? And then in my mask, I only want to have that pin change interrupt be available to me on the button pin. So it's on pin 5. So my mask is going to be all zeros except in position 5, BCN 5, so BV of position 5 here. Then I'll re-enable interrupts again now that that's all configured, right? My loop is empty. My loop does nothing now. So we basically by from a point where our loop was everything, our loop is going to contain exactly 0 code, and all of our code for toggling our LED is going to be contained in our interrupt. This is one last little tidbit for this evening. We looked last week at the enable interrupt function, right, where you gave it the name of your code, the name of the function you wanted to call, the pin, the type, falling or rising that you wanted to attach it to. When you're working with register-based interrupts and with interrupts in general, there's actually a much more general way of defining what your interrupt is, and that's this ISR function, which just says, hey, this code that follows is the interrupt service routine for a specific interrupt type. So rather than giving your function a name that you get to pick and attaching an interrupt to it, you just say, hey, this right here, this code, this is that interrupt code. So in my Arduino code here, I say ISR, and in parentheses, I tell it what kind of interrupt I want to be listening to. In this case, it's my pin change interrupt 2, right, which is what we were configuring up here. And it's pin change interrupt 2 vector. And that's just shorthand for, hey, there's a specific place in memory where this code needs to jump to. This is the number that holds where that goes. In general, you take the name of your interrupt and you append this term vector to it, _vect. And this is the terminology for the code that follows this is the interrupt service routine for the pin change to interrupt, right? And in my interrupt, all I'm doing is saying port D. Here's a construction we haven't seen before. We're saying port D equals port D exclusive ORed with the bit value corresponding to the LED, right? Which we know toggles that LED bit. So whenever that button moves from low to high or high to low, we'll trigger our interrupt service routine that's going to toggle our LED. So hopefully, if I haven't made any typos, and it wouldn't be the first time tonight that I have, when we upload this code, I toggle my button, my LED turns on and off as the button does. So basically, every time I release or press this button, that interrupt service routine is getting called and toggling that specific bit. And I press it the other way, press it or release it, it's toggling that bit again. So again, the same functionality, but in a slightly different way. This is a good chance to talk about one last little bit of construction that should be actually relatively cromulent for us. These 2 lines of code here do the same thing, but in a slightly different construction. We've looked at before constructions like, number plus equals 5, right? Which says the value of number should be increased by 5, or in other words, number should take on the value number plus 5, right? We would agree that we've seen this construction before. These are the same exact thing. You can do the same thing with bitwise math operations. So in the same way that these 2 are the same thing, these 2 lines here are the same thing. I have exclusive OR equaled this value. So port D should equal port D exclusive ORed with this value. And you can do the same thing with the various other operations. So for example, going back to our code here, we did port D equals port D or something. We could do port D or equals something. We can do port D and equals something. Pretty common construction, just say, hey, port D, I want you to take the value of port D and this other value and stuff it back into port D. Very similar to that plus equals and minus equals sort of construction that we've looked at before. I probably made a slide about that at some point, but it doesn't matter terribly much because we've seen plenty of slides tonight, I think. We done? I don't even know. Maybe I didn't. Oh yeah, I did. Here we go. Oh, well, not if I close it. Yeah, so here we go. So and equals, right, is the same thing as value equals value and x, or equals exclusive or equals. There's no such thing as not equals, because that wouldn't really make sense because there's nothing to operate on. You don't put 2 nots together, it just takes one. You can and equals and or equals and exclusive or equals, and that is the syntax for them just there. So those are some things you can do. That's one thing you can do with register access that you can't really configure using the built-in Arduino functionality and the libraries that we have available. Just to rattle off a couple more things that you can do, and some cool ways that some cool ways that this became very relevant to me in the past couple weeks. So, I mean, the whole thing, all of it revolves around the tiny moving light for me these days, right? And the classes are important, but that's the project on my workbench. But I want to share with you something cool that turned out to be surprisingly connected to this class. So, these tiny moving lights take DMX, right, as we talked about before. And I had always been under the impression, the wrong impression, that the DMX library used some kind of timer under the hood. That it was basically like every, I don't know, millisecond or microsecond, looking at the signal line, determining if it was high or low, and then figuring out, whether a new 1 or 0 had started. Because DMX timing is relatively standard, but there's some jiggery-pokery going on with a long break at the start of it, and I just assumed it was doing some specific timing built in, and then it would be using up some of the finite number of timers that we have available in the Arduino, which we'll talk about next week. But I was wrong. It's actually doing something quite clever, both on send and receive. So let me pull up the code for that there. What's happening under the hood, and I'll zoom this in here, and it's a large library, but the takeaway is, rather than try and reinvent the wheel in receiving DMX, what it's doing is reusing the serial terminal. It's reusing the serial hardware, which is meant to send and receive data, so that makes sense. And what they've done is create an ISR, an interrupt service routine, that responds to some of the built-in interrupts around the serial monitor. There's a USART TX interrupt that is triggered whenever the serial monitor, or whenever the serial port is the word, finishes sending a byte. Literally every time it sends 8 bits, and then it throws an interrupt if you want it to, and you have to basically go into the registers and enable it and say it's not enabled by default. You just say, hey, I would like you to throw me an interrupt whenever you're done sending a byte. And what the DMX library does is say, okay, I'm going to listen for that interrupt, and based on what state I know I'm in, whether I'm supposed to be sending a break in between packets, or the start byte of my code, or an actual byte of data in my code, or whether things are done, I'm going to take some specific action. And similarly, if there is an interrupt that can be triggered by whenever you receive a byte, right? And similarly, this library is enabling reception of that interrupt, listening to every single byte that comes in, and as soon as it does, it can start making some judgments about what it should do with that byte, right? So it doesn't have to do any timing on its own. It just basically listens for that interrupt, that it is gone into the configuration registers and specifically enabled and told it under what conditions it wants to receive that interrupt, because there's some more parameters in the serial port, like only show packets that are addressed to me, only show packets that have a particular encoding, which DMX kind of breaks because it's not really a serial port. And so basically the library goes in, and I wish I had bookmarked the place in the library where it does this, but maybe it's at the top if we're very lucky. Basically goes in and configures those various bytes by hand. It's somewhere in the constructor here. I'm not going to try and hunt for it now. But that's the sort of thing you can do once you start getting into accessing registers. Now, to your point, Dad, going back to the very beginning, here's our code that toggles an LED on or off when we press a button, and over the course of the last 2.5 hours, I've turned it into this. Is this code better than this code? I'm going to argue for this application, for this simple example, this code is better. It takes a little bit more space in the Arduino. It takes a little bit more time to run. But for a simple example like this, keeping it readable is really important. But when you start running into issues of space constraints or time constraints, or you want to configure options for your program that you don't have available to you sort of through the stock Arduino libraries, that's when we start needing this sort of deep register access to be able to control these parameters, if that makes sense. I know we haven't gotten into the totally satisfying examples that we can do with this, because the meat and potatoes of it is, some of the inter-chip communication protocols are really fun to look at. But honestly, the component that has the most registers associated with it is the timer modules. Even just casually glancing through, these OCR registers all deal with timers. TCC, R1, and RC are all timer-based. TMSK, PCMSK, A TMSK is all timer-based. Watchdog is a timer-based thing. So like a lot of the interrupts deal with how do we set up these various timers. And a timer, as you recall, is a counter. Essentially, it's counting up automatically for us. And that's the focus of next week, so I promise I will make that more formal. How do we set them up? What speed do they count at? And there's like 16 different interrupts that they can throw at various states in them, and so configuring when and how and what those interrupts do is a really powerful way to start getting functionality out of the Arduino. And again, some of this is taken care of for us by the basic libraries, but some of it is not, and I'm excited to share that with you. Questions? Really, like, fair game for like any more like why the hell did we talk about this for 2.5 hours? Like that's fair. The honest answer is partly because I'm a math nerd and I like talking about like bit shifts and bitwise operations because that's kind of fun. But yes, more questions while I manually mute myself with the mouse like it's, you know, March and take a sip of beer and take some more questions if there are any. And I unmuted myself this time. My power supply is not involved this week, so like that's I feel like really helping me out to not have to have too many things to remember. Yeah, no, so fair, a dense week and worth absorbing and worth going in. Check out the code on the website on the Electronics Bash. Play around with like the values and the variables. Play around with that BV macro and see like what values pop out of it when you start playing with it. This is one of those things like once you start working with it, I think will become pretty intuitive pretty quickly. And this is the long explanation. This is the nerdy explanation of it because I think it's important to know what's happening on under the hood. Happy to jump back into the shallow end for a while, says Chris. Yeah, for sure. Like this is the of this 3-week saga of hardware interrupts, register math, and timer registers. This is easily the most abstract of the 3 weeks, right? And the least application based. This is kind of it's kind of the two towers of this saga, right? Where like we left off strong with the fellowship over here, and now I've got to kind of tell you about the history of the horse lords for a little while, so that when they come to Gondor's rescue next week, you'll feel the full emotional weight and impact of their actions, if that sort of makes any sense to you nerds, which I suspect it does. Yeah, timers are really cool. Timers are really powerful. They are what underlie so many of the functions that we already know and love in Arduino. Servo, the servo library, the millis function, the micros function, pulse width modulation, analog write is based around timers, right? So that's going to give us some really cool things to like look at and understand, and some really tangible examples that are already built in that we can look at, and then we'll see some more cool stuff that we can build on top of that. Paul said I didn't have enough beer breaks. Yeah, well, talking about math, like there's only, you gotta say 1 and 0 a lot, and that takes up a lot of time. But speaking of taking up a lot of time, I see it is 9:30 Central Time, and that means I think it is time that we wrap things up for this week, y'all. Thank you for sticking with a pretty nerdy, in-depth week, I know. And I know that it didn't have the most genuine payoff. But, you know, Frodo is in Shelob's lair, but Sam is right outside the door crying for Elbereth. He's ready, and next week we're going to shine light into that cave and really take it on. Nate's on a cross-country train next Sunday. That's exciting. If you're listening along in a reception, that sounds fantastic. I want to hear about your train journey. I've done that train journey the opposite direction to California. I hope yours is smooth and good, and your weather is kind, because that makes a huge difference. Yeah, I'm excited to get into Mordor and throw a ring into the fire with you. This is going to be a fun metaphor for me, I think. As always, thank you so much. I appreciate you. If you have questions, comments, issues, concerns, feel free to leave a comment on the YouTube video or find me on Twitter at Jeffers Glass. Next stream will be next Sunday night at 7 p.m. Central Daylight Time. The topic will be timers and timer interrupts. Will be a lot of fun. As always, I appreciate so much seeing so many friendly and new faces here these weeks. It really does give me a lot of energy and strength and excitement and nerdy things. And I like it a lot, and as always, I hope it is a place of enjoyment and learning and fun, and also a place where like we who have the privilege to be on these things in these evenings can draw strength of to go out and make the world a better place in the rest of our time. You are all great. You are all a bunch of nerds, and I like you a lot. Please stay safe out there. Please wash your hands. Please hydrate. I know I'm going to, and I will see you next Sunday night. Thank you so much, everybody.